AWS Redshift migration failures and fixes. Why these incidents matter.
Modern data warehouse migrations fail silently far more often than they fail loudly. Row counts pass, dashboards load, pipelines stay green. Yet weeks or months later, teams discover something far worse than downtime. They no longer know which data to trust or whether rollback is even possible. This series documents 130-plus real-world migration incidents observed during source to Amazon Redshift migrations. These are not generic mistakes or best practices gone wrong. Each incident explains what broke, why it looks safe, when rollback quietly stopped being viable, and what forward fix looks like once trust is fractured. The central lesson is simple but uncomfortable. Rollback is not a button. It is a contract, and most migrations break it without realizing when.
Why this 130-plus incidents is split into two parts.
Covering all 130-plus incidents in a single video would blur the most important boundary in migrations, the moment rollback stops being real. This series is split deliberately. Part 1 focuses on incidents where rollback still appears possible. Engineers believe they are being careful, but hidden assumptions are already collapsing. Rollback exists in theory, but is quietly being poisoned. Part 2 focuses on incidents where rollback is provably dead. Authority has leaked externally, or system state can no longer be reconstructed. At that stage, only containment and forward fix remain. This split mirrors real migrations. Teams do not lose rollback suddenly. They cross the boundary without noticing.
Part 1, the rollback illusion.
Part 1 focuses on the most dangerous phase of any migration, when everything looks controlled but invariants are already broken. These incidents share a common pattern. Systems are partially cut over. CDC is running or paused temporarily. Validation is passing. Rollback is still assumed to be available, but underneath, authority, time, and identity are already diverging. By the end of Part 1, you will understand why many migrations fail before anyone declares success, and why rollback often fails even when no one has used it yet.
Part 1, categories and number of scenarios.
Part 1 covers the following categories. 1. Partial cutover state incidents, 7 scenarios. 2. CDC boundary and checkpoint corruption incidents, 10 scenarios. 3. Dual write inconsistency incidents, 7 scenarios. 4. Temporal consistency incidents, 7 scenarios. 5. Validation blind spot incidents, 9 scenarios. These categories represent the phase where rollback still looks possible but is already eroding.
Category 1, partial cutover state incidents.
Partial cutover incidents occur when migration progress outpaces authority decisions. BI, reporting, or read traffic is moved to Redshift while writes continue elsewhere. Teams assume CDC will maintain consistency, but no system is formally declared authoritative. These failures are dangerous because nothing breaks immediately. Divergence accumulates silently, validations pass temporarily, and trust collapses long after leadership believes the migration is complete.
Partial cutover state incidents covered.
In this category, we analyze the following real-world Redshift migration failures. 1. Partial cutover with BI pointing to Redshift while writes continue on the source system. 2. Domain-wise cutover where some schemas migrate while others remain on the source. 3. Historical data loaded into Redshift while incremental data continues on the source. 4. Dual-run validation windows extended beyond safe limits. 5. Read traffic split between source systems and Redshift. 6. Source schema evolving during an active partial cutover. 7. Redshift schema frozen while upstream source schemas continue to change.
Real-world incident during source to Redshift migration 1. BI cutover completed, while source remains write-enabled.
During an AWS Redshift migration, BI dashboards were repointed to Redshift to begin business validation. However, the source transactional system remained fully write-enabled for production applications. This created a partial cutover state where analytics and operations no longer shared a single authoritative system. Failure class. Partial cutover state incident.
System state before failure, very important.
At the moment the failure was introduced, the system state looked like this. 1. Source system, fully write-enabled and continuing to accept production transactions. 2. Redshift cluster, read-only for applications but actively queried by BI tools. 3. CDC pipeline, running continuously with acceptable lag streaming changes from source to Redshift. 4. BI and reporting tools fully reported to Redshift and publishing numbers to business users. 5. Source of truth not formally declared. Operational systems assumed source, analytics assumed Redshift. 6. Authority status ambiguous. No system was explicitly designated as authoritative. Rollback feasibility is already compromised the moment authority becomes ambiguous. Split brain state, no single source of truth. Look at the left box, the source system is green and accepting writes, evolving the business state. In the center, the CDC pipeline shows a warning because it is replicating data but lacks authority. On the right, Redshift is now the read target for all analytics. Now, look at the red timeline at the bottom. The authority line is physically broken. This gap indicates that the truth has been split. You can no longer answer a simple question like, what is our current revenue? Because the answer depends on which box you ask.
Incident analysis and root cause.
Here is the forensic narrative of how the authority breakdown occurred. 1. What action triggered it? Reporting production BI dashboards to Redshift while the source system remained fully write-enabled, intending to validate data under real user load before the final cutover. 2. Why it initially looked safe, early row count validation matched exactly across systems, and the CDC pipeline maintained minimal lag, creating the false illusion of a perfectly synchronized environment. 3. What teams noticed first? Business units reported subtle discrepancies in real-time KPIs, where operational screens showed new orders that simply had not appeared in the analytical reports yet. 4. How divergence accumulated silently. Every new write to the source without a formal freeze created a split brain state. Temporal consistency broke as the reporting layer lagged behind the transactional reality, making a single source of truth impossible.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it produces false confidence. Monitoring shows healthy CDC replication, dashboards load successfully, and validation checks appear clean. The issue surfaces only later, when business decisions rely on reports that represent a different point-in-time reality than operational systems. Detection latency for this failure is typically measured in days or weeks.
What exactly broke? Consistency breakdown.
Authoritative and temporal consistency are both broken. The system enters a split brain state where the source is authoritative for writes, while Redshift is authoritative for analytics. There is no single system that can answer with certainty what the true state of the business was at any given moment. The blast radius is unbounded, impacting all domains consumed by BI.
Rollback viability checklist, go or no go.
Before deciding on rollback, the architect must quickly assess. 1. Has Redshift accepted any direct writes from applications? No safe to discard. 2. Have BI reports been shared for regulatory decisions? Yes, high risk of distrust. 3. Has the source system changed after BI cutover? Yes, data has diverged. 4. Has any downstream system persisted Redshift-derived data? Unknown needs audit. 5. Is authoritative ownership of data clearly documented? No project failure. Rollback is technically possible, but organizational trust is already damaged.
Decision point, rollback versus forward fix.
From a purely technical standpoint, rollback is still possible because Redshift has not accepted writes and the source system remains intact. However, because BI outputs may already have influenced decisions, leadership may resist rollback. The architect must therefore prepare both rollback and forward fix paths simultaneously.
Rollback architecture, if executed.
Rollback requires repointing all BI tools back to the source system, invalidating all reports generated during the partial cutover window, and discarding the Redshift validation data. CDC must be paused, a fresh snapshot taken, and replication restarted from a known, documented checkpoint to restore both data correctness and authority.
Containment and forward fix strategy, when rollback is blocked.
Even if rollback is possible, containment is mandatory. 1. Immediately freeze source writes or place the system into controlled read-only mode. 2. Formally declare a single provisional source of truth to stop authority drift. 3. Disable or watermark BI dashboards to prevent further business decisions. 4. Audit all downstream consumers that may have cached or persisted Redshift data. 5. Plan a clean recut over with explicit governance approval and validation gates. Containment always comes before repair. Repair without authority only deepens divergence.
Preventive architecture, how this could have been avoided.
This incident is prevented by enforcing a strict rule. Analytics never move before transactional authority is frozen or dual right safeguards are in place. A time-boxed validation window using immutable snapshots, combined with an explicit declaration of source of truth, eliminates silent split-brain conditions.
Interview framing, extremely important.
In interviews, explain that partial BI cutovers without freezing rights create split-brain systems. Emphasize that rollback is not just a data operation, but a restoration of authority and trust. Highlight that low CDC lag does not guarantee correctness.
Follow-up 1. Why doesn't low CDC lag guarantee correctness here?
Answer: CDC lag measures freshness, not authority. Even perfectly up-to-date replication cannot guarantee that analytics and operations are observing the same point-in-time reality.
Follow-up 2. When does rollback stop being viable in this scenario?
Answer: rollback becomes infeasible once BI outputs are consumed externally, persisted downstream, or used in irreversible business actions such as regulatory filings or automated decisions.
Follow-up 3. Curveball. What if leadership refuses rollback despite inconsistencies?
Answer: at that point, the architect must declare Redshift authoritative, contain further rights, and execute a forward-fix strategy focused on reconciliation and trust rebuilding.
Pro insider tip.
If no one can clearly answer which system is authoritative right now, the migration has already failed, regardless of data correctness.
Real-world incident during source to Redshift migration 2. Domain-wise cutover leaves, cross-domain analytics inconsistent.
During a phased AWS Redshift migration, only a subset of business domain schemas were migrated to Redshift, while others continued operating exclusively on the source system. BI queries joined migrated and non-migrated domains, creating silent analytical inconsistencies. Failure class: partial cutover state incident.
System state before failure, very important.
At the time the failure was introduced, the system state was 1. Source system fully write-enabled, hosting several core business schemas not yet migrated. 2. Redshift cluster hosting a subset of domains already loaded and exposed for analytics. 3. CDC pipeline actively replicating only migrated schemas, non-migrated schemas excluded. 4. BI tools executing cross-domain queries assuming logical completeness. 5. Source of truth fragmented, some domains authoritative in Redshift, others only in source. 6. Authority status implicitly split by schema but never formally declared. Authority fractured by domain is still authority loss, just harder to see.
Incident analysis and root cause.
This is how the inconsistency was introduced and propagated. 1. What action triggered it? Migrating high-value fact tables first while leaving reference and dimension schemas behind to accelerate perceived progress. 2. Why it initially looked safe, individual domain-level reports validated correctly, and row counts for migrated tables matched expectations. 3. What teams noticed first? Cross-domain metrics, for example, revenue by region, customer lifetime value, began producing partial or contradictory results. 4. How divergence accumulated silently. Joins across domains span systems with different freshness, authority, and completeness, producing logically valid but semantically incorrect analytics.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it produces internally consistent but externally wrong results. Queries execute successfully, aggregates compute cleanly, and dashboards appear stable. Detection latency is typically weeks, often surfacing only during reconciliation, audits, or executive reviews. This is a classic case of the partial domain completeness illusion.
What exactly broke? Consistency breakdown.
Domain level and referential consistency are broken. Some domains exist only in Redshift, others only in the source. No system can guarantee complete joins across domains. The blast radius is unbounded for any analytical question that spans multiple schemas, making Redshift analytically unreliable despite correct individual tables.
Rollback viability checklist, go or no go.
The architect must quickly assess rollback feasibility. 1. Has Redshift accepted rights? No tables are analytics only. 2. Have partial domain reports been distributed? Yes, high confusion risk. 3. Are non-migrated domains still evolving in source? Yes, divergence ongoing. 4. Have downstream systems cache-joined results? Unknown, audit required. 5. Is there a single declared authoritative system? No, domain split authority rollback remains possible, but analytical trust is already fractured.
Decision point, rollback versus forward fix.
Rollback is technically viable because Redshift has not accepted writes and the source remains intact. However, because business users have already consumed cross-domain analytics, rollback alone may not restore trust. The architect must decide whether to revert analytics entirely or contain damage while completing migration.
Rollback architecture, if executed.
Rollback requires disabling all cross-domain analytics, repointing BI tools fully back to the source system, and discarding Redshift domain tables used for partial reporting. Migration must restart with a domain-complete snapshot strategy to ensure referential and analytical consistency.
Containment and forward fix strategy, when rollback is blocked.
If rollback is rejected, containment becomes mandatory. 1. Immediately disable or restrict cross-domain joins in BI tools. 2. Formally declare Redshift non-authoritative until all dependent domains are migrated. 3. Complete migration of remaining domains using a synchronized snapshot window. 4. Rerun cross-domain validations only after domain completeness is guaranteed. 5. Communicate analytical limitations clearly to business stakeholders. Partial domains are worse than partial data. They create believable lies. Here is Redshift SQL showing how federated joins create silent temporal inconsistency during domain-wise cutover. Disclaimer: always test code in a non-production environment. Here is the federated join that breaks rollback safety. This line combines two domains that are at different migration states. Redshift contains a CDC-lagged snapshot, while the external Oracle schema reflects real-time truth. Once this join is used, no point-in-time rollback can recreate the same analytical result. Here is the semantic corruption point. This predicate filters historical sales using current inventory state. Valid historical transactions are silently excluded if stock has since depleted, creating analytically incorrect KPIs that still pass row count and checksum validation. Here is where the damage becomes irreversible. Aggregates computed on mixed-time data cannot be reconciled via CDC replay or snapshot restore, because the original filtering context no longer exists in either system.
Preventive architecture, how this could have been avoided.
Domain-wise cutovers must be treated as all or nothing for analytics. Either migrate all dependent domains together or explicitly block cross-domain reporting. Declaring domain completeness as a gating criterion prevents false analytical confidence.
Interview framing, extremely important.
In interviews, explain that partial domain migration breaks referential integrity even when individual tables validate correctly. Emphasize that analytics require domain completeness, not just data freshness.
Follow-up 1. Why don't row counts detect this issue?
Answer: row counts validate tables in isolation. The failure occurs at join boundaries, where missing domain members cause silent row loss during query execution.
Follow-up 2. When does rollback stop being viable here?
Answer: rollback becomes impractical once partial domain analytics influence decisions, or are embedded into downstream models or reports that cannot be easily invalidated.
Follow-up 3. Curveball. What if business demands early domain analytics anyway?
Answer: the architect must enforce analytical guardrails, limiting queries to single domain scopes and clearly labeling outputs as incomplete until domain migration is finished.
Pro insider tip.
If two domains answer to two different systems, your analytics no longer describe a business. They describe a migration artifact.
Real-world incident during source to Redshift migration 3. Historical data loaded into Redshift, while incremental writes continue only on source.
During an AWS Redshift migration, a full historical snapshot was successfully loaded into Redshift for validation. However, incremental CDC replication was intentionally delayed or paused, while the source system continued to accept new transactions. This created a temporal split where Redshift contained a frozen past and the source contained an advancing present. Failure class: partial cutover state incident.
System state before failure, very important.
At the moment the inconsistency was introduced, the system state was 1. Source system fully write-enabled, continuing to accept new transactions. 2. Redshift cluster loaded with a complete historical snapshot up to a fixed cutoff time. 3. CDC pipeline paused or not yet started for incremental replication. 4. BI tools pointed to Redshift for validation and early reporting. 5. Declared source of truth, implicitly Redshift for analytics, source for operations. 6. Authority status, split across time, Redshift owns the past, source owns the present. This state guarantees a time gap even if no errors are reported.
Incident analysis and root cause.
This failure unfolded quietly due to an architectural assumption. 1. Triggering action, completing a full historical load into Redshift while deferring CDC activation to a later phase. 2. While it looked safe initially, historical row counts matched perfectly and validation queries passed for past periods. 3. What teams noticed first? Reports for recent hours or days showed missing revenue or activity compared to operational dashboards. 4. How divergence accumulated. Every new transaction written to the source after the snapshot cutoff widened the unseen temporal gap.
Why this failure is dangerous, hidden risk.
This failure creates false confidence because nothing is technically broken. Queries succeed, tables are complete, and historical validations pass. The danger lies in the invisible time window between the snapshot cutoff and the present, where business activity exists only in the source system. Detection latency is typically measured in hours or days, depending on reporting frequency.
What exactly broke? Consistency breakdown.
Temporal consistency is broken. Redshift represents a valid but incomplete timeline that ends at the snapshot cutoff, while the source system continues forward. There is no single system that can answer questions spanning both past and present without manual reconciliation. All time-based analytics are unreliable beyond the cutoff point.
Rollback viability checklist, go or no go.
A fast rollback assessment reveals: 1. Has Redshift accepted application rights? No snapshot-only state. 2. Has CDC started and advanced offsets? No clean restart possible. 3. Has the source changed post-snapshot? Yes, time gap exists. 4. Have BI outputs been externally published? Possibly, requires audit. 5. Is authoritative ownership clearly defined? No, time-sliced authority rollback is technically clean, but trust depends on how long the gap existed.
Decision point, rollback versus forward fix.
Rollback remains the preferred option if the time gap is short and BI outputs can be invalidated. If the gap spans critical business periods or reports were consumed externally, a forward fix may be required to reconcile the missing window, instead of discarding Redshift data entirely. Here is Redshift SQL showing how a snapshot cutoff creates a silent temporal data gap during migration. Disclaimer: always test code in a non-production environment. Here is the cutoff marker. This value represents the frozen point in time captured by the historical snapshot. Any business activity after this timestamp exists only in the source system and is completely absent from Redshift analytics.
Containment and forward fix strategy.
If rollback is delayed or rejected, containment is mandatory. 1. Immediately pause BI consumption for time ranges beyond the snapshot cutoff. 2. Declare the source system authoritative for all post-cutoff reporting. 3. Start CDC from a clearly documented offset aligned to the snapshot end time. 4. Backfill the missing window explicitly before re-enabling analytics. 5. Revalidate aggregates spanning the cutoff boundary before restoring trust. Never attempt reconciliation while authority remains split across time.
Preventive architecture, how this could have been avoided.
This incident is avoided by enforcing a hard rule. Snapshots and CDC must form a continuous timeline with no gaps. Either freeze source writes during snapshot or start CDC before snapshot completion, with a guaranteed overlap window.
Interview framing, extremely important.
In interviews, explain that a historical snapshot without immediate CDC creates a time travel bug. Emphasize that perfect historical accuracy is meaningless if the present is missing, and that rollback decisions depend on the size and impact of the temporal gap.
Follow-up 1. Why do row counts still pass in this scenario?
Answer: row counts validate completeness of the snapshot, not continuity of time. They provide no signal about missing future events after the snapshot cutoff.
Follow-up 2. When does this become a forward fix-only situation?
Answer: when the gap spans financial close periods, regulatory windows, or externally published reports. Discarding Redshift becomes more damaging than reconciling the missing interval.
Follow-up 3. Curveball. Can CDC always fix this gap later?
Answer: only if the source still retains the required change history. If logs expire or retention windows close, the gap becomes permanent.
Pro insider tip.
A snapshot without an immediate CDC bridge is not a migration. It is a paused timeline waiting to break trust.
Real-world incident during source to Redshift migration 4. Dual-run validation window, extended beyond safe limits.
During an AWS Redshift migration, teams intentionally ran both the source system and Redshift in parallel to validate data correctness. However, the dual-run window was extended far beyond its original scope due to repeated validation delays and business hesitation. Over time, this transformed a temporary safety mechanism into a long-lived split-brain architecture. Failure class: partial cutover state incident.
System state before failure, very important.
The system entered the failure state gradually with the following characteristics. 1. Source system, fully write-enabled and operational for all transactions. 2. Redshift cluster continuously refreshed and queried for validation and reporting. 3. CDC pipeline actively replicating changes to Redshift with acceptable lag. 4. BI tools alternating between source and Redshift depending on report and user. 5. Source of truth, temporarily undefined by design but never formally resolved. 6. Authority status, permanently ambiguous due to prolonged dual run. Dual run is only safe when time-boxed. Once extended, it becomes architectural debt. Architecture diagram showing dual run drift over time. This diagram illustrates the timeline of failure. On the left, the planned cutover is green. As we move right into the extended validation zone, the color shifts to yellow or red. The divergence icons accumulate over time, showing how fixes applied to the source are not perfectly replicated to Redshift, creating a trust drift that makes a clean cut over mathematically impossible.
Incident analysis and root cause.
This failure did not occur suddenly. It emerged through inaction. 1. Triggering condition: repeated postponement of the final cutover due to minor validation discrepancies and business risk aversion. 2. Why it initially looked safe: parallel systems allowed teams to compare reports and build confidence incrementally. 3. What teams noticed first: different teams began quoting different numbers depending on which system they trusted. 4. How divergence accumulated over time: schema changes, fixes, and compensations were applied asymmetrically, making the systems logically similar but never identical.
Why this failure is dangerous, hidden risk.
This failure creates the illusion of safety. Because both systems are live and producing results, teams believe they can always reconcile later. In reality, prolonged dual run guarantees drift. Detection latency is extremely high because discrepancies are normalized as expected differences rather than treated as migration failures.
What exactly broke? Consistency breakdown.
Authoritative consistency is broken. No system is ever formally declared the single source of truth. Over time, business processes, fixes, and interpretations diverge, making rollback and forward fix equally risky. The blast radius expands with time, eventually impacting every downstream consumer.
Rollback viability checklist, go or no go.
A prolonged dual run severely degrades rollback feasibility. 1. Has Redshift accepted analytical trust? Yes, widely used. 2. Has the source system changed independently? Yes, continuous. 3. Have fixes or compensations diverged? Likely over time. 4. Is there a clean validation baseline? No, moving target. 5. Can authority be restored cleanly? No, politically hard. Rollback may be technically possible, but trust rollback is no longer achievable.
Decision point, rollback versus forward fix.
At this stage, rollback becomes a theoretical option only. The longer the dual run persists, the more the organization becomes dependent on Redshift outputs. Forward fix with formal authority declaration is usually the only viable path.
Containment and forward fix strategy.
Since rollback is politically blocked, containment is mandatory. 1. Issue a source of truth mandate. Declare Redshift as the master for all analytical decisions starting immediately. 2. Freeze the source. Stop allowing operational teams to backpatch legacy data. 3. Execute a delta repair load. Resync any tables that drifted during the dual run window. 4. Decommission the legacy read path. Physically block BI tools from accessing the old database to force alignment. You cannot validate forever. At some point, you must commit to the new reality.
Preventive architecture, how this could have been avoided.
Dual run must always be time-boxed with a hard exit date. Validation criteria should be predefined, automated, and binding. If criteria are met, cutover proceeds by rule, not by comfort level.
Interview framing, extremely important.
In interviews, explain that dual run is a safety net, not a steady state. Emphasize that extending it increases risk rather than reducing it, and that indecision is itself an architectural failure.
Follow-up 1. Why does extending a dual run window increase risk instead of reducing it?
Answer: because validation stops being a point-in-time comparison and becomes a moving target. As time passes, fixes, schema changes, and compensations occur independently in each system. This silently destroys the ability to establish a single authoritative baseline.
Follow-up 2. When does rollback stop being viable in a prolonged dual run?
Answer: rollback stops being viable once teams and business processes begin trusting Redshift outputs operationally. Even if data can be restored, authority cannot be rolled back once decisions, fixes, or narratives diverge across systems.
Follow-up 3. Curveball. What if leadership insists on keeping dual run indefinitely for safety?
Answer: that is a governance failure, not a technical one. The architect must escalate that indefinite dual run guarantees permanent split brain. At that point, declaring authority and forcing cutover is safer than pretending validation still exists.
Pro insider tip.
Before starting dual run, lock a non-negotiable exit date and validation checklist approved by engineering and business. If the date slips even once, stop validation immediately and force an authority decision. Prolonged dual run always causes more damage than an early cutover or rollback.
Real-world incident during source to Redshift migration 5. Read traffic split across source and Redshift via load balancer.
During an AWS Redshift migration, read traffic was intentionally split between the source system and Redshift using DNS rules and load balancer routing. The goal was to gradually shift analytical reads while minimizing risk. Instead, this created a non-deterministic read path where identical queries returned different results depending on which system handled the request. Failure class: partial cutover state incident.
System state before failure, very important.
At the time the failure state emerged, the system topology was 1. Source system fully write-enabled and continuing to mutate transactional state. 2. Redshift cluster actively queried for analytics and ad hoc reads. 3. Traffic routing, DNS or load balancer rules randomly or conditionally routing read traffic. 4. CDC pipeline running continuously with acceptable lag. 5. BI tools, some queries routed to Redshift, others still hitting the source. 6. Source of truth implicitly assumed, never formally declared. 7. Authority status fragmented, authority depended on routing outcome. Routing logic replaced governance and silently fractured authority.
Load balancer or DNS routing logic. How this failure was technically introduced.
Read traffic was split using DNS-based routing and load balancer rules rather than a formal cutover. Some clients resolved the source endpoint, while others resolved the Redshift endpoint based on TTL, client location, or routing weights. Because DNS resolution and load balancers operate outside application and data governance, identical read requests were transparently served by different systems without any signal to users or monitoring.
Why load balancers break data authority during migration?
This routing strategy introduces failure modes that are invisible at the application layer. 1. DNS caching causes different clients to resolve different data sources for the same logical query. 2. Load balancers optimize availability and latency, not correctness or point-in-time consistency. 3. Routing decisions are made per request or per session, not per business transaction. 4. Neither system knows when it is being bypassed, so no consistency guardrails can activate. 5. Rollback is delayed because DNSTTLs and client caches cannot be invalidated instantly. Infrastructure routing creates probabilistic truth, not authoritative truth.
Incident analysis and root cause.
This failure was introduced through infrastructure convenience rather than data design. 1. Triggering action, introducing DNS or load balancer rules to gradually shift read traffic to Redshift. 2. While it initially looked safe, both systems returned valid-looking results and no errors were observed. 3. What teams noticed first, users reported inconsistent results when refreshing dashboards or rerunning the same query. 4. How divergence accumulated. Each system answered queries based on a different point-in-time view of the business, and routing decisions masked the inconsistency.
Why this failure is dangerous, hidden risk.
This failure creates probabilistic correctness. The same query can return different answers depending on routing, cache state, or timing. Monitoring does not fail because both systems are healthy individually. Detection latency is high, often surfacing only when executives compare numbers side by side.
What exactly broke? Consistency breakdown.
Authoritative and temporal consistency are broken. There is no single system responsible for answering analytical questions. Instead of one truth, the architecture produces multiple plausible truths. The blast radius is unbounded because every consumer behind the load balancer is affected.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Has Redshift accepted direct writes? No, rollback technically possible. 2. Has DNS or routing propagated globally? Yes, hard to unwind instantly. 3. Have business decisions used Redshift-derived results? Likely. 4. Is routing logic fully auditable? Often no. 5. Can authority be re-established cleanly? Yes, with forceful governance. Rollback restores routing, but not trust lost during inconsistent reads.
Decision point, rollback versus forward fix.
Rollback is technically feasible by reverting all read traffic back to the source. However, because inconsistent answers may already have influenced decisions, leadership often resists reverting. This pushes the architect toward containment and forward fix instead of a clean rollback.
Containment and forward fix strategy.
When rollback is blocked, containment must happen immediately. 1. Disable split routing and force all reads to a single system. 2. Formally declare the authoritative read source even if imperfect. 3. Invalidate cached results and force dashboard refreshes. 4. Communicate a temporary trust freeze to business users. 5. Rerun validation using one canonical system only. 6. Plan a controlled recutover after authority and consistency are restored. You cannot reconcile data while reads are non-deterministic.
Preventive architecture, how this could have been avoided.
Read traffic must never be split across systems during migration. Gradual cutover must be time-based or audience-based, not query-based. Either all reads go to the source or all reads go to the target. Anything in between guarantees inconsistency.
Interview framing, extremely important.
In interviews, explain that load balancers solve availability problems, not consistency problems. Emphasize that routing logic cannot replace data authority, and that probabilistic reads are worse than downtime during migration.
Follow-up 1. Why is splitting read traffic worse than dual-run validation?
Answer: dual run at least preserves deterministic answers per system. Split reads make correctness probabilistic, where the same query yields different results with no signal of which is correct.
Follow-up 2. When does rollback become ineffective here?
Answer: rollback becomes ineffective once inconsistent results have been cached, exported, or acted upon by business workflows that cannot be undone.
Follow-up 3. Curveball. What if leadership insists split reads reduce risk?
Answer: risk is reduced only for uptime, not correctness. The architect must explain that silent data inconsistency is a higher business risk than temporary unavailability.
Pro insider tip.
Never let infrastructure teams control data authority through routing rules. Load balancers don't understand truth, only traffic.
Real-world incident during source to Redshift migration 6. Source schema evolves while cutover is in progress.
During an AWS Redshift migration, the transactional source system continued to evolve while the migration cutover was in progress. New columns and data type changes were deployed in the source schema, but Redshift remained frozen to preserve migration stability. This caused silent structural divergence between systems while CDC continued to replicate data. Failure class, partial cutover state incident.
System state before failure, very important.
At the time schema divergence was introduced, the system state was 1. Source system write-enabled with ongoing schema deployments by application teams. 2. Redshift cluster schema frozen to maintain migration validation stability. 3. CDC pipeline actively replicating data without schema change enforcement. 4. BI tools reading exclusively from Redshift. 5. Source of truth implicitly assumed to be Redshift for analytics. Source for writes. 6. Authority status, ambiguous structural authority not governed. Schema drift during cutover silently invalidates all downstream validation.
Incident analysis and root cause.
Failure unfolded through a common migration blind spot. 1. Triggering action application teams deployed schema changes, new columns, and altered data types during the migration cutover window. 2. Why it initially looked safe, CDC continued running successfully and no load failures were reported. 3. What teams noticed first, reports showed missing or null values for newly introduced business attributes. 4. How divergence accumulated. Data landed in Redshift without corresponding structural representation, silently discarding or truncating fields.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it does not break pipelines. CDC continues to replicate rows successfully, masking the fact that schema evolution has already invalidated data completeness. Detection latency is typically weeks, discovered only when new attributes are referenced by business logic or reports.
What exactly broke? Consistency breakdown.
Structural and domain-level consistency are broken. The source system contains a richer schema than Redshift, meaning analytical truth is incomplete. Redshift becomes untrustworthy for any domain impacted by the schema change, and no single authoritative model exists.
Rollback viability checklist, go or no go.
Schema divergence materially affects rollback feasibility. 1. Has Redshift accepted writes? No safe. 2. Has source schema changed post-cutover? Yes. Structural drift. 3. Can historical data be reloaded cleanly, only with schema alignment? 4. Are BI outputs structurally incomplete? Yes. 5. Is authoritative schema documented? No. Rollback restores data, not lost structure, unless schema is reconciled.
Decision point, rollback versus forward fix.
Rollback is technically possible but incomplete without schema reconciliation. Forward fix is often chosen to avoid re-snapshotting large datasets, but only after schema authority is re-established and drift is explicitly corrected.
Containment and forward fix strategy.
Schema authority must be restored before any data repair. 1. Immediately freeze source schema changes until migration authority is restored. 2. Compare source and Redshift DDL histories to identify drift windows. 3. Apply missing DDL changes to Redshift explicitly, never rely on implicit CDC behavior. 4. Reload affected tables or partitions to backfill structurally lost data. 5. Rerun validation only after schema parity is confirmed. Data correctness without schema correctness is meaningless. Here is Redshift system table, SQL, showing how post-cutover schema changes can be detected via STL_DDL_log. Disclaimer: always test code in a non-production environment. This system table records all DDL executed inside Redshift. The absence of expected alter statements during the cutover window confirms that schema changes never reached Redshift. Here is SQL used to compare source and Redshift column definitions to expose silent schema drift. Disclaimer: always test code in a non-production environment. Running this query on both source and Redshift reveals missing or mismatched columns, proving structural divergence even when row counts appear correct.
Preventive architecture, how this could have been avoided.
All schema changes must be governed during migration. Either freeze schema evolution entirely or enforce dual deployment with automated parity checks. CDC alone is never sufficient to manage structural change.
Interview framing, extremely important.
In interviews, explain that data migration without schema governance creates silent corruption. Emphasize that CDC guarantees movement, not completeness, and that schema authority must be explicitly controlled during cutover.
Follow-up 1. Why doesn't CDC fail when schema changes occur?
Answer: CDC focuses on row movement, not schema parity. If new columns are ignored or truncated, replication can still succeed while silently dropping business-critical data.
Follow-up 2. When does rollback stop being viable in this scenario?
Answer: rollback becomes risky once new schema-driven data is written only in the source and consumed by business logic, making historical reconstruction incomplete.
Follow-up 3. Curveball. What if schema changes are urgent and cannot be frozen?
Answer: then migration authority is already lost. The architect must pause cutover, rebaseline schemas, and restart validation, not continue forward blindly.
Pro insider tip.
If schema governance is not enforced, your migration is already invalid, even if every pipeline is green.
Real-world incident 7. Redshift schema frozen while source schema changes.
During an AWS Redshift migration, the target schema was intentionally frozen to stabilize validation. However, the source system introduced a breaking change, for example, changing order_ID from integer to alphanumeric. As CDC loads continued, Redshift began rejecting data due to type mismatches, causing massive ingestion failures. Failure class: partial cutover state incident.
System state before failure.
When the failure condition emerged, the system state was 1. Source system write enabled with active schema deployments. 2. Redshift cluster schema explicitly frozen for migration stability. 3. CDC pipeline actively loading data but failing on specific columns. 4. BI tools reading from Redshift reporting partial data. 5. Authority status structurally inconsistent and undocumented. A frozen target schema only works if the source is frozen too.
Incident analysis and root cause.
This incident followed a predictable but often missed path. 1. Triggering action: application teams changed a data type into varchar in the source. 2. While it initially looked safe, CDC jobs continued running, but specific rows were rejected silently or logged to error tables. 3. What teams noticed first: missing orders in Redshift that existed in source because they contained alphanumeric characters. 4. Root cause: Redshift is schema on-write. It enforces the old schema, rejecting valid new business data.
Why this failure is dangerous?
This failure is dangerous because it mixes loud and silent errors. If max_errors is set high in the copy command, Redshift will skip the bad rows and load the rest. You end up with a dataset that is 99% complete but missing the newest, most critical business transactions.
Rollback viability checklist.
1. Has Redshift accepted partial loads? Yes, data gaps. 2. Has source schema changed? Yes, structural drift. 3. Can failed rows be replayed? Yes, if CDC logs exist. Verdict: rollback not required, but deep fix is mandatory.
Decision point: deep copy versus patch.
You cannot simply patch this in Redshift. Redshift does not support changing a column data type in place easily. You must execute a deep copy, rebuild strategy. Detection: finding the type mismatch and load errors. Disclaimer: always test code in a non-production environment. This error is the smoking gun. It means the source sent an alphanumeric string, for example, ord55, but Redshift is still trying to force it into an integer column. The fix: performing a deep copy to alter data types. Disclaimer: always test code in a non-production environment. Because Redshift cannot alter column types in place for populated tables, we must perform a deep copy. We migrate the data to a staging table with the new schema, then swap the names. This is the only way to heal the structural drift.
Preventive architecture.
Schema evolution must be governed during migration. If the source changes, the migration pipeline must have an automated schema drift detection step that pauses the loader before data is rejected.
Interview framing.
In interviews, use this to demonstrate deep Redshift knowledge. Explain that schema drift in Redshift is expensive, requires table rebuilds compared to other DBs, which is why freezing the source schema is a critical architectural requirement.
Follow-up 1. Why don't we just use max_errors 1000 to ignore the bad rows?
Answer: ignoring errors creates data loss. Those 1000 rows aren't bad data, they are new business reality. Ignoring them corrupts the integrity of the data warehouse.
Follow-up 2. What is the downside of the deep copy fix?
Answer during the insert into. Select, the table effectively doubles in storage and I or O usage. If the table is 50 terabytes, this operation can take days and lock the cluster.
Follow-up 3, curveball. Can we use Redshift Spectrum to bypass this?
Answer, yes. If we offload the data to S3 Parquet, Redshift Spectrum handles schema evolution, schema on read, much more gracefully than native storage. This is a valid workaround for volatile schemas.
Pro Insider tip.
If copy errors appear during cutover, assume schema authority is already broken, not that the data is merely malformed.
Category 1 wrap-up. Why partial cutovers fail quietly.
All partial cutover state incidents share one root problem. Authority is never formally transferred. The system continues to function, data continues to move, and dashboards continue to load, but correctness is no longer guaranteed. These failures rarely trigger alarms because nothing is technically broken. What breaks is trust. Once authority is ambiguous, rollback becomes political, validation becomes subjective, and every downstream decision is compromised.
Transition from authority failures to data movement failures.
So far, every incident involved two systems being live at the same time. Now we move into a more dangerous class of failures, where even after authority is decided, data movement itself lies to you. In the next category, the systems look stable, CDC appears healthy, and dashboards load normally, yet the data is already corrupted. These are CDC boundary failures, and they are among the hardest migration issues to detect and recover from.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs in a single zip file, containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, system design. Required for your data engineer interviews jobs like data quality analyst jobs, data governance analyst jobs, AWS Python data engineer jobs, AWS Redshift database administrator DBA jobs, AWS Glue ETL developer jobs, AWS data engineer jobs, cloud data engineer jobs, data architect jobs, DataOps engineer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Category 2, CDC boundary and checkpoint corruption.
CDC boundary and checkpoint corruption incidents occur when migration activities interrupt, restart, or overlap change data capture in unsafe ways. Unlike partial cutovers, authority may be clearly declared, but the continuity of data is broken. These failures exploit assumptions about offsets, ordering, and transactional completeness. Once violated, CDC can silently reapply, skip, or reorder changes, permanently corrupting analytical truth.
CDC boundary and checkpoint corruption. Incidents covered.
In this category, we will analyze the following real-world migration incidents. 1. CDC offset lost during migration freeze, when replication restarts without a reliable checkpoint. 2. CDC resumes from wrong LSN or SCN, replaying or skipping data due to incorrect recovery position. 3. CDC replay causes duplicate application when idempotency assumptions fail after restart. 4. Deletes missed during cutover window, leaving ghost records that pass row count validation. 5. Out-of-order CDC events applied, breaking temporal and transactional consistency. 6. Snapshot and CDC overlap window misaligned, mixing full load and incremental data incorrectly. 7. CDC started before Snapshot completed, allowing partial history to be overwritten. 8. CDC started after Snapshot cutoff, permanently missing changes during the gap. 9. Partial transaction commits replicated, violating atomicity across systems. 10. Source undo or segment expiration during long loads, silently losing historical changes. In CDC failures, the system looks healthy until you ask the wrong question and get the wrong answer.
Real-world incident during source to Redshift migration 8. CDC offset, lost during migration freeze.
During an AWS Redshift migration, the CDC pipeline was paused to support a controlled freeze window. When replication was later resumed, the task restarted without a verified checkpoint, silently replaying historical changes instead of resuming from the correct offset. This introduced duplicate and conflicting records, making rollback unsafe without deep reconciliation. Failure class, CDC boundary and checkpoint corruption.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system, write-enabled and continuing transactional activity. 2. Redshift cluster loaded with snapshot data and accepting CDC-applied changes. 3. CDC pipeline paused during freeze and manually resumed afterward. 4. Replication checkpoint not explicitly recorded or validated before restart. 5. BI tools pointed to Redshift for early validation and reporting. 6. Declared source of truth not formally re-established after freeze. 7. Authority status temporarily suspended and never explicitly restored. A CDC pause without a verified checkpoint creates an invisible restart boundary.
Incident analysis and root cause.
The incident occurred through the following sequence. 1. Triggering action, stopping the CDC task during a freeze without persisting the exact resume offset. 2. Why it appeared safe, the CDC task restarted successfully and showed healthy lag metrics. 3. What teams noticed first, gradual appearance of duplicate business records in Redshift. 4. What teams did not notice that CDC had replayed already applied source changes. 5. How divergence accumulated. Each replay compounded duplicates while validations focused on row growth. 6. Missing invariant, exactly once CDC resumed from a verified replication checkpoint.
Why this failure is dangerous, hidden risk.
This failure is dangerous because CDC replay looks identical to normal catch-up behavior. Replication metrics remain green, lag decreases, and no alarms fire. The corruption is semantic, not operational. Detection latency is typically days or weeks, surfacing only when aggregates drift or reconciliation is attempted.
What exactly broke? Consistency breakdown.
Transactional and temporal consistency are broken, resulting in a duplicated timeline where the same business events exist more than once. Redshift is no longer a trustworthy projection of source history, and no single authoritative truth exists. If we roll back only data, this inconsistency remains because the original CDC offset boundary is unknown and cannot be reconstructed from snapshots.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Has Redshift accepted CDC applied rights? Yes, duplicate state already exists. 2. Is the original CDC offset known with certainty? No, restart boundary lost. 3. Can duplicates be deterministically isolated, sometimes business key dependent? 4. Have downstream systems consumed this data? Likely trust impact persists. 5. Can authority be re-established cleanly after restore? Only with reconciliation and governance. Rollback without a known offset restores state, not correctness.
Decision point, rollback versus forward fix.
Rollback is no longer clean because the replication boundary is unknown. Restoring snapshots would reintroduce ambiguity unless CDC history is replayed perfectly. Forward fix with controlled deduplication and authority reassertion becomes the only viable path.
Code illustration and Redshift artifacts.
In this section, we will show 1. How CDC task state is inspected to prove checkpoint loss. 2. Why CDC restart without a verified offset makes rollback unsafe. Rollback is shown to explain the boundary. It was not executed due to lost authority. Here is Bodo 3 showing how CDC task statistics expose loss of a valid resume checkpoint. Disclaimer, Always test code in a non-production environment. This snippet proves whether a valid CDC resume checkpoint exists. Missing or reset checkpoint fields confirm that the task cannot safely resume from its prior position. Here is Bodo 3 showing how restarting CDC without a preserved offset causes replay instead of resume. Disclaimer: always test code in a non-production environment. This restart assumes the checkpoint is correct. When that assumption is false, CDC replays historical changes, proving why rollback cannot rely on CDC resume.
Containment and forward fix strategy.
Once checkpoint loss is confirmed, containment must precede repair. 1. Immediately pause CDC to stop further duplicate application. 2. Declare Redshift non-authoritative for affected domains. 3. Identify and reconcile duplicates using business keys and timestamps. 4. Reseed CDC from a newly documented snapshot boundary. 5. Re-enable analytics only after reconciliation completes. CDC checkpoints are authority, not metadata.
Follow-up 1. Why doesn't CDC alert when an offset is lost?
Answer: because replaying data is still valid replication from the tool perspective. The corruption is logical, not operational.
Follow-up 2. When did rollback stop being safe in this incident?
Answer: rollback stopped being safe the moment CDC replayed changes beyond an unknown boundary, making original history unrecoverable.
Follow-up 3. What single rule would have prevented this failure?
Answer: never pause CDC without recording and validating the exact resume checkpoint against the source system.
Pro insider tip.
If you cannot prove a CDC restart boundary before resuming replication, treat the pause as a destructive event and plan reconciliation, not rollback.
Real-world incident during source to Redshift Migration 9. CDC resumed from wrong LSN or SCN after restart.
During an AWS Redshift migration, the CDC pipeline was stopped during a maintenance or freeze window and later restarted. Although the replication task resumed successfully, it restarted from an incorrect LSN or SCN position, skipping some committed changes and replaying others. This silently corrupted data completeness and invalidated rollback assumptions. Failure class: CDC boundary and checkpoint corruption.
System state before failure, very important.
At the moment the failure was introduced, the system state was: 1. Source system write enabled with continuous transactional commits. 2. Redshift cluster loaded via snapshot and accepting CDC applied changes. 3. CDC pipeline restarted after stop without validating LSN or SCN alignment. 4. Replication checkpoint present but incorrect relative to source commit history. 5. BI tools pointed to Redshift for validation and early reporting. 6. Declared source of truth not formally re-established after restart. 7. Authority status assumed intact but already compromised. A valid-looking checkpoint is not the same as a correct checkpoint.
Incident analysis and root cause.
The failure occurred through the following sequence. 1. Triggering action, restarting CDC after a stop without validating the resume LSN or SCN against the source. 2. Why it appeared safe, the CDC task resumed normally and reported healthy lag metrics. 3. What teams noticed first, missing records and duplicated updates appearing days later. 4. What teams did not notice that CDC resumed from an incorrect commit boundary. 5. How divergence accumulated, some source transactions were skipped while others were replayed. 6. Missing invariant, exactly once CDC resumed from a verified LSN or SCN boundary.
Why this failure is dangerous, hidden risk.
This failure is dangerous because CDC health metrics remain green while correctness degrades. Lag improves, tasks remain running, and validation focuses on growth rather than completeness. Detection latency is typically days or weeks, surfacing only during reconciliation or audit.
What exactly broke? Consistency breakdown.
Transactional and temporal consistency are broken, resulting in a fractured timeline where some committed source changes never reach Redshift while others appear more than once. Redshift is no longer a trustworthy projection of source history, and no single authoritative truth exists. If we roll back only data, this inconsistency remains because the original commit boundary cannot be reconstructed from snapshots or CDC state.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Has Redshift accepted CDC applied rights? Yes, corrupted state already applied. 2. Is the correct LSN or SCN known with certainty? No, boundary incorrect. 3. Can skip changes be deterministically identified? No, gaps are silent. 4. Have downstream systems consumed this data? Likely trust impact persists. 5. Can authority be re-established cleanly after restore? Only with reconciliation and governance. Rollback without a correct boundary restores state, not truth.
Decision point, rollback versus forward fix.
Rollback is unsafe because the correct resume boundary is unknown. Restoring snapshots would reintroduce ambiguity unless all missing changes are reconstructed. Forward fix with reconciliation and authority reassertion becomes the only viable option.
Code illustration and Redshift artifacts.
In this section, we will show 1. How CDC task statistics expose the active LSN or SCN position. 2. Why restarting CDC from an incorrect boundary makes rollback unsafe. Rollback is shown to explain the boundary. It was not executed due to lost authority. Here is Bodo 3 showing how CDC task statistics expose incorrect LSN or SCN resume positions. Disclaimer: always test code in a non-production environment. This snippet exposes the internal resume position of the CDC task. A mismatch between these values and the source commit position proves that CDC resumed from an incorrect LSN or SCN. Here is Bodo 3 showing how restarting CDC without validating LSN or SCN alignment invalidates rollback safety. Disclaimer: always test code in a non-production environment. This restart assumes the checkpoint is correct. When the LSN or SCN is wrong, CDC silently skips or replays changes, proving why rollback cannot rely on CDC resume.
Containment and forward fix strategy.
Once boundary corruption is confirmed, containment must occur first. 1. Immediately pause CDC to prevent further divergence. 2. Declare Redshift non-authoritative for affected domains. 3. Reconcile missing and duplicated records using source of truth extracts. 4. Reseed CDC from a newly verified snapshot boundary. 5. Re-enable analytics only after reconciliation completes. CDC correctness depends on boundary truth, not task uptime.
Follow-up 1. Why doesn't CDC fail when it resumes from the wrong LSN or SCN?
Answer: because from the tool perspective replication is still valid. The corruption is logical, not operational, so health metrics remain green.
Follow-up 2. When did rollback stop being safe in this scenario?
Answer: rollback stopped being safe the moment CDC applied changes from an incorrect boundary, because original commit history became unrecoverable.
Follow-up 3. What single architectural rule would have prevented this?
Answer: CDC must resume exactly once from a verified LSN or SCN boundary validated against the source system.
Pro insider tip.
Never restart CDC unless you can prove the resume LSN or SCN against the source at that moment. A green restart proves nothing about correctness.
Real-world incident during source to Redshift migration 10. CDC replay causes duplicate application after resume.
During an AWS Redshift migration, CDC was stopped and later resumed. Due to replay from an earlier boundary, previously applied changes were ingested again. This produced duplicate business records, broke idempotency, and invalidated clean rollback assumptions. Failure class: CDC boundary and checkpoint corruption.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system write-enabled with immutable business keys. 2. Redshift cluster loaded via snapshot and accepting CDC-applied changes. 3. CDC pipeline restarted and replayed historical changes. 4. Checkpoint state present but replayed from an earlier boundary. 5. BI tools consuming Redshift outputs. 6. Declared source of truth, implicitly Redshift for analytics. 7. Authority status, assumed intact but already violated. Replay is indistinguishable from resume without idempotency.
Incident analysis and root cause.
The failure unfolded as follows. 1. Triggering action restarting CDC after a stop with replay from an earlier boundary. 2. Why it appeared safe, CDC health metrics were green and lag reduced quickly. 3. What teams noticed first, gradual metric inflation and duplicate records. 4. What teams did not notice, reapplied historical events. 5. How divergence accumulated, each replay compounded duplicates over time. 6. Missing invariant, exactly once apply with enforced idempotency.
Why this failure is dangerous, hidden risk.
This failure is dangerous because pipelines succeed while semantics break. Counts grow, lag shrinks, and dashboards look healthy. Detection latency is days or weeks, surfacing during reconciliation or audit.
What exactly broke? Consistency breakdown.
Transactional consistency is broken due to duplicate application of the same logical events. Redshift no longer represents a single, linear history of source commits. If we roll back only data, this inconsistency remains because the replay boundary cannot be cleanly separated from valid changes without idempotent keys.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Has Redshift accepted CDC applied rights? Yes, duplicates exist. 2. Is the replay boundary precisely known? Often no. 3. Are duplicates deterministically identifiable? Depends on business keys. 4. Have downstream systems consumed the data? Likely. 5. Can authority be re-established cleanly after restore? Only with deduplication. Rollback without idempotency restores volume, not correctness.
Decision point, rollback versus forward fix.
Rollback is risky when replay boundaries are mixed with valid changes. Forward fix with deterministic deduplication and authority reassertion is required to restore correctness.
Code illustration and Redshift artifacts.
In this section, we will show 1. How duplicate application is detected. 2. How replay manifests at the data level. 3. What rollback would require at the system boundary. 4. How forward fix deduplication restores correctness. This scenario requires full code because mechanics determine safety. Here is Redshift SQL showing how CDC replay creates duplicate business keys. Disclaimer: always test code in a non-production environment. This snippet proves duplicate application. Multiple rows for the same business key confirm that CDC replayed historical events instead of resuming exactly once. Here is Redshift SQL showing how replay inflates aggregates despite valid joins. Disclaimer: always test code in a non-production environment. This result indicates silent inflation. Aggregates remain syntactically correct, while semantic truth is violated by duplicated facts. Here is Bodo 3 showing how CDC restart from replayed boundary invalidates rollback safety. Disclaimer: always test code in a non-production environment. This restart assumes exactly once semantics. When replay occurs, rollback cannot rely on CDC state to reconstruct a clean boundary. Here is Redshift SQL showing a deterministic deduplication forward fix using business keys. Disclaimer: always test code in a non-production environment. This window function enforces idempotency. By partitioning by the business key order_ID and selecting the latest event, we restore exactly once semantics even if the source sent duplicates during migration catch-up.
Containment and forward fix strategy.
Once duplication is confirmed, containment precedes repair. 1. Immediately pause CDC to stop further replay. 2. Declare Redshift non-authoritative until deduplication completes. 3. Apply deterministic deduplication with auditability. 4. Reseed CDC from a verified snapshot boundary. 5. Re-enable analytics after revalidation. Idempotency is the only cure for replay.
Follow-up 1. Why didn't row counts flag this earlier?
Answer: because counts increase monotonically. Replay adds rows without violating basic completeness checks.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once replayed changes mixed with downstream consumption, erasing a clean boundary.
Follow-up 3. What single design choice would have prevented this?
Answer: enforcing idempotent apply using immutable business keys at ingestion.
Pro insider tip.
If CDC can replay, your warehouse must be idempotent by design. Exactly once is an invariant you enforce, not a feature you assume.
Real-world incident during source to Redshift migration 11. Deletes missed during cutover window.
During an AWS Redshift migration, CDC replication lagged across a cutover window where deletes occurred in the source system. Inserts and updates were applied, but deletes were missed or delayed, leaving ghost rows in Redshift that no longer existed in the source. Failure class: CDC boundary and checkpoint corruption.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system writes enabled, deletes occurring during cutover window. 2. Redshift cluster loaded via snapshot and receiving CDC changes. 3. CDC pipeline running with lag, delete events not yet applied. 4. Checkpoint state advancing but not validated for delete completeness. 5. BI tools pointed to Redshift for validation and reporting. 6. Declared source of truth, implicitly Redshift for analytics. 7. Authority status, assumed intact without delete validation. Delete completeness is an invariant, not an assumption.
Incident analysis and root cause.
The failure emerged from a blind spot in CDC validation. 1. Triggering action proceeding with cutover while CDC lag existed for delete events. 2. Why it appeared safe, row counts increased as expected and no CDC errors were reported. 3. What teams noticed first, reports included records that should have been removed. 4. What teams did not notice, missing delete propagation across the boundary. 5. How divergence accumulated, each missed delete left durable ghost rows in Redshift. 6. Missing invariant, delete parity between source and target at the cutover boundary.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it preserves plausible but false data. Pipelines are green, counts grow, and joins succeed. Detection latency is typically days or weeks, surfacing during reconciliation or audit when records should not exist at all.
What exactly broke? Consistency breakdown.
Referential and domain-level consistency are broken due to durable ghost rows. Redshift answers questions with entities that no longer exist in the source. If we roll back only data, this inconsistency remains because delete events were never applied and cannot be reconstructed without a precise delete ledger.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Has Redshift accepted CDC applied rights? Yes, ghost rows exist. 2. Are delete events fully captured and replayable? Often no. 3. Is the delete boundary precisely known? Rarely. 4. Have downstream systems consumed ghost rows? Likely. 5. Can authority be restored by restore alone? No, deletes missing. Restoring volume without deletes preserves false history.
Decision point, rollback versus forward fix.
Rollback is often meaningless because restoring snapshots does not recreate missing delete intent. Forward fix requires explicit delete reconciliation and authority reassertion rather than blind restore.
Code illustration and Redshift artifacts.
In this section, we will show 1. How ghost rows are detected by comparing source and target state. 2. Why rollback is not shown because it would not restore delete intent. Detection proves irreversibility. Mechanics add no safety here. Here is Redshift SQL showing how ghost rows are detected after missed deletes. Disclaimer: always test code in a non-production environment. This snippet proves the existence of ghost rows. Records present in Redshift but absent in the source confirm that delete events were missed during the cutover window.
Containment and forward fix strategy.
Once ghost rows are confirmed, containment must precede repair. 1. Freeze analytics that depend on affected entities. 2. Declare the source authoritative for delete truth. 3. Reconcile deletes using source-side ledgers or tombstones. 4. Apply controlled delete backfills with audit trails. 5. Revalidate referential integrity before restoring trust. Deletes define absence. Absence must be proven, not assumed.
Follow-up 1. Why didn't row counts detect this?
Answer: row counts measure presence, not absence. Missed deletes inflate correctness while passing basic validations.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once delete intent was lost, and downstream consumers acted on ghost rows.
Follow-up 3. What single control would have prevented this?
Answer: a mandatory delete parity check at cutover with a hard block on proceed.
Pro insider tip.
If deletes are not explicitly validated at cutover, assume your warehouse contains entities the business has already erased.
Real-world incident during source to Redshift migration 12. Out-of-order CDC events applied after resume.
During an AWS Redshift migration, CDC replication was paused during a cutover window and later resumed. When replication restarted, change events were applied out of order, causing older updates to overwrite newer state. The pipeline remained healthy, but business data regressed silently. Failure class, CDC boundary and checkpoint corruption.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system write enabled, generating high-frequency updates on the same rows. 2. Redshift cluster receiving CDC applied changes post-resume. 3. CDC pipeline paused and resumed without ordering validation. 4. Checkpoint state present but not enforcing event ordering. 5. BI tools actively querying Redshift for validation. 6. Declared source of truth, assumed Redshift after resume. 7. Authority status, implicitly trusted without temporal guarantees. Checkpoint presence does not guarantee correct event order.
Incident analysis and root cause.
This failure resulted from an incorrect assumption about CDC replay semantics. 1. Triggering action, resuming CDC after a pause without validating event ordering. 2. Why it appeared safe, CDC resumed successfully and lag metrics recovered quickly. 3. What teams noticed first, attribute values unexpectedly reverting to older states. 4. What teams did not notice, update events arriving out of temporal order. 5. How divergence accumulated, older events overwrote newer state during replay. 6. Missing invariant, monotonic event time ordering per primary key.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it produces valid-looking but historically incorrect data. No errors occur, row counts remain stable, and CDC health appears normal. Detection latency is often days, surfacing only when business logic depends on the latest state.
What exactly broke? Consistency breakdown.
Temporal and transactional consistency are broken due to non-monotonic update application. Redshift no longer represents the latest state of entities. If we roll back only data, this inconsistency remains because the event ordering information required to restore correct state has already been lost.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Has Redshift accepted CDC applied rights? Yes, state overwritten. 2. Is original event order recoverable? No, ordering lost. 3. Can last write wins be reconstructed deterministically? Rarely. 4. Have downstream systems consumed regress state? Likely. 5. Would snapshot restore fix ordering? No, replay repeats issue. Rollback without ordering guarantees recreates the same corruption.
Decision point, rollback versus forward fix.
Rollback is unsafe because restoring data does not restore event order. Forward fix is required, focusing on reasserting correct ordering constraints and repairing affected entities based on authoritative source state.
Code illustration and Redshift artifacts.
In this section, we will show 1. How out-of-order updates are detected using event timestamps. 2. Why ordering constraints must exist before replay or repair. Ordering proof establishes why mechanics alone cannot fix this. Here is Redshift SQL showing how out-of-order CDC updates are detected per business key. Disclaimer: always test code in a non-production environment. This snippet proves out-of-order application. A newer update was applied before an older one, confirming that CDC replay violated monotonic event time ordering and corrupted latest state semantics.
Containment and forward fix strategy.
Once ordering violations are confirmed, containment must precede repair. 1. Pause CDC to stop further out-of-order application. 2. Declare the source system authoritative for latest state. 3. Recompute entity state using strict event time ordering. 4. Reapply updates using deterministic last write rules. 5. Enforce ordering constraints before resuming CDC. State repair. Without ordering enforcement guarantees, repeat failure.
Follow-up 1. Why didn't CDC health metrics catch this?
Answer: CDC health metrics track throughput and lag, not correctness of ordering. From the system's perspective, all events were applied successfully. The corruption occurs at the semantic layer, where event time meaning is silently violated.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once out-of-order updates overwrote newer state and downstream consumers read that regressed data. At that point, restoring snapshots would simply replay the same ordering failure again.
Follow-up 3. What invariant must always be enforced to prevent this?
Answer: monotonic event time ordering per business key must be enforced at apply time. Without it, CDC correctness depends on luck rather than guarantees, especially across pause and resume boundaries.
Pro insider tip.
If you cannot prove that updates for the same key are applied in strict event time order, you do not have CDC correctness. You only have data movement.
Real-world incident during source to Redshift migration 13. Snapshot and CDC overlap window misaligned.
During an AWS Redshift migration, a full snapshot load and CDC replication were configured with an assumed overlap window. Due to misaligned timing, some changes were applied twice while others were skipped, creating silent inconsistencies that passed initial validation. Failure class, CDC boundary and checkpoint corruption.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system write enabled during snapshot execution. 2. Redshift cluster loading snapshot data while CDC was enabled. 3. CDC pipeline started with an assumed overlap window. 4. Overlap boundary not explicitly measured or validated. 5. BI tools querying Redshift after snapshot completion. 6. Declared source of truth assumed Redshift post load. 7. Authority status assumed correct without overlap proof. Overlap assumptions without measurement create silent gaps.
Incident analysis and root cause.
This failure originated from implicit timing assumptions. 1. Triggering action enabling CDC with a presumed snapshot overlap window. 2. Why it appeared safe snapshot completed successfully and CDC showed low lag. 3. What teams noticed first occasional metric discrepancies across time ranges. 4. What teams did not notice, duplicate, or missing events around the overlap boundary. 5. How divergence accumulated. Overlap misalignment caused double apply and skip patterns. 6. Missing invariant, approvable, continuous timeline between snapshot end and CDC start.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it produces selectively incorrect data. Most records are correct, validations pass, and dashboards look stable. Detection latency is often weeks, surfacing only when historical reconciliation or audit compares narrow time windows.
What exactly broke? Consistency breakdown.
Temporal consistency is broken due to an unproven overlap boundary. Redshift contains a timeline with hidden gaps and overlaps. If we roll back only data, this inconsistency remains because the exact overlap window cannot be reconstructed after the fact.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Has Redshift accepted CDC applied rights? Yes, mixed state exists. 2. Is the exact snapshot end time recorded? Often no. 3. Is CDC start offset provably aligned? No, assumed only. 4. Have downstream systems consumed affected ranges? Likely. 5. Would restore plus replay recreate correct timeline? No, boundary unknown. Rollback without a known overlap boundary recreates ambiguity.
Decision point, rollback versus forward fix.
Rollback is unsafe because replaying snapshot and CDC without a provable overlap recreates the same temporal gaps. Forward fix must focus on detecting and repairing affected windows rather than full restore.
Code illustration and Redshift artifacts.
In this section, we will show 1. How a narrow time window query exposes overlap gaps or duplicates. 2. Why rollback is not shown because the overlap boundary is unknowable. One proof is enough when the boundary itself is missing. Here is Redshift SQL showing how snapshot and CDC overlap gaps are detected in a narrow time window. Disclaimer: always test code in a non-production environment. This snippet isolates the assumed overlap window. Missing or duplicated events in this narrow range prove that snapshot and CDC timelines were not continuous, confirming misalignment.
Containment and forward fix strategy.
Once overlap misalignment is confirmed, containment must precede repair. 1. Freeze analytics for affected time windows. 2. Declare the source system authoritative for overlap periods. 3. Identify duplicate and missing events using source logs. 4. Repair data window by window with full auditability. 5. Require explicit overlap validation before future cutovers. Time windows must be proven, not assumed.
Follow-up 1. Why did initial validation pass?
Answer: initial validation focused on total volume and broad aggregates. Overlap errors affect narrow time slices, which are statistically invisible unless explicitly tested. This allows the issue to survive early checks unnoticed.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once the overlap window was not explicitly recorded. Without knowing where snapshot ended and CDC began, any replay recreates uncertainty instead of restoring truth.
Follow-up 3. What single control prevents this class of failure?
Answer: a mandatory overlap proof that shows continuous event time coverage between snapshot end and CDC start. Without that proof, cutover must be blocked regardless of perceived readiness.
Pro insider tip.
If you cannot draw the snapshot to CDC handoff as a single uninterrupted timeline, you already have a temporal corruption, even if every dashboard looks correct.
Real-world incident. During source to Redshift migration 14, CDC started before snapshot completed.
During an AWS Redshift migration, CDC replication was started before the full snapshot load had completed. This caused some rows to be applied twice, while others were overwritten by the snapshot, creating silent inconsistencies that passed early validation. Failure class: CDC boundary and checkpoint corruption.
System state before failure. Very important.
At the moment the failure was introduced, the system state was: 1. Source system fully write-enabled and generating ongoing changes. 2. Redshift cluster actively loading a full snapshot. 3. CDC pipeline started before snapshot completion. 4. CDC offset position advancing concurrently with snapshot load. 5. BI tools disabled or pointed to Redshift for early checks. 6. Declared source of truth, assumed Redshift post-snapshot. 7. Authority status, implicitly assumed without sequencing guarantees. CDC and snapshot running together breaks ordering guarantees.
Incident analysis and root cause.
This failure was caused by incorrect sequencing assumptions. 1. Triggering action starting CDC replication before snapshot load completion. 2. Why it appeared safe, CDC lag appeared minimal and snapshot showed steady progress. 3. What teams noticed first, inconsistent aggregates across short time ranges. 4. What teams did not notice, rows applied by CDC being overwritten by snapshot inserts. 5. How divergence accumulated, concurrent writes violated load ordering guarantees. 6. Missing invariant, snapshot completion must strictly precede CDC start.
Why this failure is dangerous. Hidden risk.
This failure is dangerous because it produces non-deterministic results. Some CDC-applied changes survive. Others are silently lost when the snapshot writes later rows. Detection latency is typically weeks, discovered only when reconciling specific records.
What exactly broke? Consistency breakdown.
Transactional and temporal consistency are broken. The same source event may or may not exist in Redshift depending on load timing. If we roll back only data, this inconsistency remains because execution order between snapshot and CDC cannot be reconstructed.
Rollback viability checklist. Go or no go.
Before rollback is considered, the architect must evaluate. 1. Has Redshift accepted CDC applied writes? Yes, mixed execution state. 2. Did snapshot overwrite CDC applied rows, likely ordering violated? 3. Is execution ordering provable post facto? No, timing lost. 4. Have downstream systems consumed affected data? Possible, audit required. 5. Would replay guarantee correctness? No, same race condition. Rollback recreates the race unless sequencing is corrected.
Decision point. Rollback versus forward fix.
Rollback is unsafe because replaying snapshot and CDC in the same order recreates non-determinism. Forward fix must focus on identifying and repairing overwritten or missing records.
Code illustration and Redshift artifacts.
In this section, we will show 1. How timestamp analysis reveals overwritten or missing CDC-applied rows. 2. Why rollback is not shown because sequencing cannot be recovered. Sequencing failures require proof, not replay. Here is Redshift SQL showing how CDC-applied rows were overwritten by snapshot execution. Disclaimer: always test code in a non-production environment. This snippet isolates records that appear only once but whose update timestamps indicate CDC application before snapshot overwrite, proving data lost due to incorrect sequencing.
Containment and forward fix strategy.
Once sequencing failure is confirmed, containment must precede repair. 1. Immediately stop CDC to prevent further race conditions. 2. Declare the source system authoritative for the affected window. 3. Identify overwritten changes using source logs. 4. Backfill missing changes with controlled re-ingestion. 5. Enforce strict snapshot before CDC sequencing in future runs. Order is a contract, not an optimization.
Follow-up 1. Why didn't CDC errors surface immediately?
Answer: CDC did not fail operationally because both Snapshot and CDC were valid processes. The failure was logical ordering, which monitoring does not capture. As a result, the issue surfaced only during later reconciliation.
Follow-up 2. When did Rollback stop being safe?
Answer: Rollback stopped being safe once Snapshot and CDC overlapped in execution. At that point, execution order was non-deterministic, and replaying cannot guarantee restoration of the original event sequence.
Follow-up 3. What single rule would have prevented this?
Answer: a hard rule that CDC must never start until snapshot completion is verified and logged. This invariant eliminates race conditions entirely and preserves a single authoritative timeline.
Pro insider tip.
If Snapshot and CDC overlap even briefly, assume some changes were lost. Ordering bugs never announce themselves, they hide in timing.
Real-world incident. During source to Redshift migration 15, CDC started after snapshot cutoff.
During an AWS Redshift migration, a full snapshot was completed and validated, but CDC replication was started after the snapshot cutoff time. Changes that occurred between snapshot completion and CDC start were never captured, creating a permanent data gap that looked like normal historical completeness. Failure class: CDC boundary and checkpoint corruption.
System state before failure. Very important.
At the moment the failure was introduced, the system state was: 1. Source system fully write-enabled and generating ongoing changes. 2. Redshift cluster snapshot completed and validated successfully. 3. CDC pipeline started after snapshot completion. 4. CDC offset position initialized after snapshot cutoff. 5. BI tools enabled and pointing to Redshift for validation. 6. Declared source of truth, assumed Redshift post-snapshot. 7. Authority status, assumed without continuity guarantees. A snapshot without an immediate CDC bridge guarantees a blind window.
Incident analysis and root cause.
This failure resulted from a broken continuity assumption. 1. Triggering action starting CDC after the snapshot completed instead of before or during the cutoff window. 2. Why it appeared safe, snapshot validation passed and CDC started cleanly with no errors. 3. What teams noticed first, missing activity for a specific time range during reconciliation. 4. What teams did not notice, that no system ever captured changes in the gap window. 5. How divergence accumulated, source continued to advance while Redshift timeline skipped forward. 6. Missing invariant, snapshot and CDC must form a continuous, gap-free timeline.
Why this failure is dangerous. Hidden risk.
This failure is dangerous because it creates a clean-looking but incomplete history. All validations pass for data that exists, while missing data leaves no operational signal. Detection latency is often weeks, discovered only when auditing specific business periods.
What exactly broke? Consistency breakdown.
Temporal consistency is broken. Redshift contains 2 valid segments of time with a missing interval in between. If we roll back only data, this inconsistency remains because the missing window was never captured by any system.
Rollback viability checklist. Go or no go.
Before rollback is considered, the architect must evaluate: 1. Did snapshot complete successfully? Yes, baseline exists. 2. Did CDC start after the snapshot cutoff? Yes, gap confirmed. 3. Can missing changes be replayed from logs? Maybe retention dependent. 4. Have downstream systems consumed Redshift data? Likely trust impact persists. 5. Would snapshot restore remove the gap? No, gap predates CDC. Rollback restores state, not missing history.
Decision point. Rollback versus forward fix.
Rollback is not meaningful because restoring the snapshot recreates the same missing window. Forward fix must focus on reconstructing the gap from source logs or accepting permanent data loss.
Code illustration and Redshift artifacts.
In this section, we will show: 1. How timestamp comparisons expose the missing snapshot to CDC window. 2. Why rollback is not shown because the gap cannot be eliminated by restore. Continuity gaps are detected, not repaired by rollback. Here is Redshift SQL showing a missing time window between snapshot completion and CDC start. Disclaimer: always test code in a non-production environment. This snippet identifies the latest timestamp present in Redshift. Comparing it with the source system proves a silent gap where changes were never ingested.
Containment and forward fix strategy.
Once a missing window is confirmed, containment must precede repair. 1. Pause trust in Redshift for the affected time range. 2. Declare the source system authoritative for the missing interval. 3. Attempt gap reconstruction from source redo or archive logs. 4. Backfill only after boundaries are explicitly defined. 5. Revalidate all aggregates spanning the gap window. You cannot fix what you never captured without redefining authority.
Follow-up 1. Why didn't snapshot validation catch this?
Answer: snapshot validation confirms completeness only up to the cutoff point. It provides no signal about changes that occur immediately after completion. As a result, the gap remains invisible during early checks.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe the moment CDC was initialized after the snapshot cutoff. From that point on, no system held a complete timeline, making restore ineffective.
Follow-up 3. What single control prevents this class of failure?
Answer: enforcing a mandatory overlap window where CDC starts before snapshot completion. This guarantees continuity and ensures no source changes are lost between phases.
Pro insider tip.
If you cannot draw a continuous line from snapshot start to CDC steady state, you already lost data. Continuity is a requirement, not an optimization.
Real-world incident during source to Redshift migration 16. Partial transaction commits replicated by CDC.
During an AWS Redshift migration, a multi-statement transaction in the source system was partially replicated to Redshift. CDC applied some statements before a failure occurred, but the transaction was never fully committed at the source. This broke transactional atomicity and created state that never existed in the source system. Failure class: CDC boundary and checkpoint corruption.
System state before failure, very important.
At the moment the failure was introduced, the system state was: 1. Source system write enabled with multi-statement transactions. 2. Redshift cluster accepting CDC applied changes. 3. CDC pipeline running with transactional batching enabled. 4. CDC offset position advancing during in-flight transactions. 5. BI tools pointed to Redshift for validation. 6. Declared source of truth assumed Redshift post-cutover. 7. Authority status implicitly assumed without transactional parity. CDC applied data that was never committed at the source.
Incident analysis and root cause.
This failure was caused by incorrect transactional assumptions. 1. Triggering action: CDC applied changes from a multi-statement transaction before commit confirmation. 2. Why it appeared safe: CDC lag remained low and no replication errors occurred. 3. What teams noticed first: inconsistent parent-child relationships in analytics. 4. What teams did not notice that the source transaction was rolled back. 5. How divergence accumulated: partial data persisted without rollback awareness. 6. Missing invariant: exactly once an atomic transaction apply.
Why this failure is dangerous, hidden risk.
This failure is dangerous because the data looks valid and passes basic validation. The corruption is semantic. Redshift contains state that never existed in the source. Detection latency is often weeks, discovered only when referential or financial inconsistencies surface.
What exactly broke? Consistency breakdown.
Transactional consistency is broken. Redshift reflects a partially applied transaction that was never committed. If we roll back only data, this inconsistency remains because CDC has no knowledge of source rollback boundaries.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Has Redshift accepted partial transaction rights? Yes, atomicity violated. 2. Can CDC replay identify rollback transactions? No, commit context lost. 3. Is the exact transaction boundary known? No, offset only. 4. Have downstream systems consumed inconsistent state? Likely trust impact persists. 5. Would Snapshot restore guarantee correctness? Only if taken before transactions start. Rollback without transactional context recreates inconsistency.
Decision point, rollback versus forward fix.
Rollback is unsafe unless a snapshot exists from before the transaction began. Forward fix must identify and remove orphaned partial data and reassert transactional authority.
Code illustration and Redshift artifacts.
In this section, we will show 1. How partial transactions can be detected in Redshift. 2. How CDC applies statements without commit awareness. 3. What rollback would require at the system level. 4. How forward fix restores transactional consistency. Transactional failures must be proven at execution level. Here is Redshift SQL showing orphaned rows caused by partial transaction replication. Disclaimer: always test code in a non-production environment. This snippet proves partial transaction application. Child rows exist without their parent, indicating CDC applied statements that were rolled back at the source. Here is Redshift SQL showing lack of transactional grouping in CDC applied rows. Disclaimer: always test code in a non-production environment. This snippet shows that CDC applied rows are grouped by internal transaction identifiers that do not map to source transaction boundaries, proving loss of atomicity. Here is Bodo 3 showing how CDC resumes without transaction rollback awareness. Disclaimer: always test code in a non-production environment. This restart resumes CDC from an offset, not a transaction boundary. It proves that rollback source transactions cannot be undone once partially applied. Here is Redshift SQL showing how orphaned rows from partial transactions can be safely removed during forward fix. Disclaimer: always test code in a non-production environment. This snippet removes child records that reference parent transactions which never committed at the source. This proves how forward fix restores transactional consistency by eliminating state that never legitimately existed, rather than attempting unsafe rollback.
Containment and forward fix strategy.
Once partial transaction application is confirmed, containment must precede repair. 1. Immediately stop CDC to prevent further partial applies. 2. Declare the source system authoritative for affected domains. 3. Identify orphaned or partial records using referential checks. 4. Delete or correct inconsistent rows with full audit logging. 5. Restart CDC only after transactional safety is revalidated. Transaction repair without authority control amplifies corruption.
Follow-up 1. Why didn't CDC respect source transaction rollback?
Answer: CDC operates on change streams, not full transactional semantics. Once individual statements are omitted, CDC has no awareness of later rollbacks. This causes partial application when failures occur mid-transaction.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once partial transaction data was consumed by downstream systems. At that point, restoring snapshots would remove some state but leave trust and lineage broken.
Follow-up 3. What invariant prevents this failure entirely?
Answer: enforcing exactly once atomic transaction replication. Without transactional grouping and commit awareness, CDC cannot guarantee correctness for multi-statement workloads.
Pro insider tip.
If CDC claims transactional consistency, ask how it handles rollbacks midstream. If the answer is offsets, not commits, you already know the risk.
Real-world incident during source to Redshift migration 17. Source undo or retention expired during CDC catch-up.
During an AWS Redshift migration, CDC replication was paused for an extended period to support snapshot load and validation. When CDC later resumed, the source database no longer retained sufficient undo or redo history. As a result, some historical changes were permanently lost and never replicated. Failure class, CDC boundary and checkpoint corruption.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system write enabled with finite undo or redo retention. 2. Redshift cluster loaded with snapshot data and awaiting CDC catch-up. 3. CDC pipeline paused or lagging far behind source head. 4. CDC offset position older than source retention window. 5. BI tools disabled or pointed to Redshift for validation. 6. Declared source of truth, assumed Redshift after snapshot. 7. Authority status, assumed continuity without validating source retention. CDC cannot read history that no longer exists.
Incident analysis and root cause.
This failure resulted from an invalid durability assumption. 1. Triggering action, allowing CDC lag to grow beyond the source undo or redo retention window. 2. Why it appeared safe, snapshot completed successfully and CDC showed no immediate errors. 3. What teams noticed first, missing historical updates after CDC resumed. 4. What teams did not notice that the source database had already overwritten required change history. 5. How divergence accumulated. CDC advanced offsets while silently skipping irretrievable changes. 6. Missing invariant. CDC lag must always remain within source change retention limits.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it creates permanent data loss without operational alarms. CDC continues running, offsets advance, and the system appears healthy. Detection latency is often weeks, discovered only during deep reconciliation or audit.
What exactly broke? Consistency breakdown.
Temporal and transactional consistency are broken. Some source changes no longer exist anywhere and can never be replicated. If we roll back only data, this inconsistency remains because the missing history is unrecoverable.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Did CDC lag exceed source retention limits? Yes, changes permanently lost. 2. Can missing changes be reconstructed from logs? No, logs expired. 3. Would snapshot restore recover missing history? No, snapshot predates loss. 4. Have downstream systems consumed incomplete data? Likely trust impact persists. 5. Can authority be restored cleanly? No, history irrecoverable. Rollback cannot restore data that no system retained.
Decision point, rollback versus forward fix.
Rollback is not meaningful because restoring any snapshot reproduces the same data loss. Forward fix must focus on declaring permanent loss, correcting downstream expectations, and rebuilding trust with explicit gaps acknowledged.
Code illustration and Redshift artifacts.
In this section, we will show 1. How missing changes are detected via source versus target comparison. 2. How source retention configuration proves why recovery is impossible. Retention limits define the point of no return. Here is Redshift SQL showing gaps caused by irretrievable CDC history. Disclaimer: always test code in a non-production environment. This snippet exposes the earliest and latest timestamps present in Redshift. Comparing this range to the source timeline proves that certain historical updates were never replicated. Here is source database configuration showing undo or retention limits that caused CDC data loss. Disclaimer: always test code in a non-production environment. This configuration proves that the source database retained change history for a finite window. Once CDC lag exceeded this limit, required history was overwritten, making recovery impossible.
Containment and forward fix strategy.
Once retention loss is confirmed, containment must precede repair. 1. Declare the affected time range permanently incomplete. 2. Communicate data loss explicitly to downstream consumers. 3. Rebaseline analytics to exclude irrecoverable periods. 4. Increase source retention before any future migration retries. 5. Rerun migration only after retention invariants are enforced. Acknowledging loss early preserves trust better than hiding gaps.
Follow-up 1. Why didn't CDC fail when undo expired?
Answer: CDC treats missing history as absence, not error. From the tool's perspective, there is nothing to apply. The failure is semantic, not operational, so health metrics remain green.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe the moment CDC lag exceeded source retention. At that point, no snapshot or replay could ever reconstruct the missing changes.
Follow-up 3. What single control would have prevented this?
Answer: enforcing a hard rule that CDC lag must never exceed source retention limits. Migration freezes must be bounded by retention, not by schedule convenience.
Pro insider tip.
If CDC falls behind retention, stop calling it replication. At that point, it is selective history loss with a green dashboard.
Category 2 wrap-up. Why CDC corruption is still a recoverable failure.
CDC boundary and checkpoint corruption incidents break replication correctness, but they usually preserve a single writer model. Even when offsets are lost or events are replayed incorrectly, the original business action still occurred in one authoritative system. This means rollback or controlled forward fix defix can sometimes restore consistency if boundaries are identified early. The next category moves beyond recoverable replication, failures, into a more dangerous class of incidents.
Transition from CDC corruption to dual write inconsistency.
In CDC failures, corruption occurs because changes are applied incorrectly. In dual write failures, corruption occurs because changes are created independently. The system no longer has a single version of a business event to reconcile against. Once writes succeed in different systems under different conditions, replication correctness no longer matters because the data itself has diverged at creation time.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs in a single zip file, containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, system design. Required for your data engineer interviews jobs like data quality analyst jobs, data governance analyst jobs, AWS Python data engineer jobs, AWS Redshift database administrator DBA jobs, AWS Glue ETL developer jobs, AWS data engineer jobs, cloud data engineer jobs, data architect jobs, DataOps engineer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Category 3. Dual write inconsistency incidents.
Dual write inconsistency incidents occur when applications write to both the source system and Redshift without a global transaction boundary. Each system evaluates success independently, and retry or failure handling differs across paths. This creates logically valid but mutually incompatible states. These incidents are often permanent because there is no authoritative event history to restore.
Scenarios covered in Category 3.
This category includes the following real-world failure scenarios. 1. Writes succeed in source but fail in Redshift. 2. Writes succeed in Redshift but fail in source. 3. Retry logic creates duplicate records. 4. Partial transaction replication across systems. 5. No global transaction identifier exists. 6. Application-level retries amplify divergence. 7. Business logic diverges between systems. Once dual write inconsistency begins, rollback can restore data but not business truth.
Category guidance, coding versus architecture.
In this category, code is rarely the primary teaching tool. The failure is architectural, not mechanical. SQL or scripts may be used sparingly to prove that divergence exists, but they must never imply that logic can be repaired with queries. The focus is on authority, transaction boundaries, and irreversibility.
Real-world incident during source to Redshift migration 18. Writes succeed in source but fail in Redshift.
During an AWS Redshift migration, application writes continued to succeed in the source transactional database, while the same writes intermittently failed to apply in Redshift due to load errors and CDC apply failures. The source system advanced business state, but Redshift reflected only a partial version of reality. Failure class, dual write inconsistency incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system fully write-enabled and accepting production transactions. 2. Redshift cluster accepting CDC applied changes with intermittent load failures. 3. CDC pipeline running but experiencing row-level apply errors. 4. Write path applications writing only to the source system. 5. BI tools pointed to Redshift for analytics and validation. 6. Declared source of truth, implicitly Redshift for analytics, source for operations. 7. Authority status, split by success path not formally governed. Successful writes in one system do not imply successful replication.
Incident analysis and root cause.
This incident occurred due to an invalid reliability assumption. 1. Triggering action, continuing production writes while CDC apply errors occurred in Redshift. 2. Why it appeared safe, source transactions committed successfully and CDC task remained running. 3. What teams noticed first, missing records in Redshift that were visible in the source system. 4. What teams did not notice that CDC apply failures were silently dropping individual rows. 5. How divergence accumulated. Each failed apply widened the gap between operational truth and analytical state. 6. Missing invariant. Every successful source write must be applied exactly once in the target.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it creates silent analytical incompleteness. Operational systems remain correct, CDC pipelines appear healthy, and validation focuses on growth rather than absence. Detection latency is often days or weeks, discovered only when reconciliation or audits expose missing facts.
What exactly broke? Consistency breakdown.
Transactional and domain-level consistency are broken. Redshift no longer represents a complete projection of the source system. If we roll back only data, this inconsistency remains because the source continued to advance independently while Redshift silently lost writes.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Did source writes continue successfully? Yes, source advanced independently. 2. Did Redshift miss some of those writes? Yes, apply failures occurred. 3. Is the missing set fully identifiable? No, row-level failures incomplete. 4. Have downstream systems consumed Redshift data? Likely analytics used. 5. Can authority be restored by snapshot alone? No, divergence already exists. Rollback restores state, not lost write intent.
Decision point, rollback versus forward fix.
Rollback is technically possible but rarely restores trust. Restoring Redshift snapshots does not recover missed writes unless every failed apply is re-identified and replayed. Forward fix focusing on reconciliation and authority declaration is typically required.
Rollback architecture, if executed.
Rollback must be treated as a full system reset. A cluster snapshot restore would be required to rewind Redshift to a known pre-divergence point, with all CDC streams discarded and reseeded from a verified offset. BI tools must be repointed back to the source system, caches invalidated, and all downstream artifacts rebuilt. Partial or table-level rollback is unsafe because missed writes are not domain-isolated. Governance approval is mandatory because restored data may invalidate previously consumed analytics.
Code illustration and Redshift artifacts.
In this section, we will show 1. How missing writes are detected via Redshift load error inspection. Asymmetric success must be proven, not assumed. Here is Redshift system table. SQL showing CDC apply failures that caused missing writes. Disclaimer, always test code in a non-production environment. This system table exposes rows that failed to apply in Redshift. The presence of errors here proves that successful source writes did not result in corresponding target state.
Containment and forward fix strategy.
Once asymmetric write success is confirmed, containment must precede repair. 1. Pause analytics consumption until reconciliation is complete. 2. Declare the source system authoritative for the affected window. 3. Identify missing records using source-side audit or keys. 4. Re-ingest missing data with full idempotency controls. 5. Revalidate completeness before restoring trust. Repair without authority only deepens inconsistency.
Interview framing, extremely important.
How would you explain this in an interview? Key talking points. 1. Dual write safety depends on symmetric success, not tool health. 2. CDC running does not guarantee completeness. 3. Missing writes destroy analytical authority even if operations succeed. 4. Rollback restores snapshots, not lost write intent. Key architectural principle: exactly once application is an invariant, not an optimization.
Follow-up 1. Why didn't monitoring catch this earlier?
Answer: because system health focused on pipeline uptime, not semantic completeness. CDC tasks remained running, and source commits succeeded, so no operational alarms triggered despite silent data loss in the target.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once missing writes were mixed with downstream analytics. At that point, snapshots could not distinguish between never applied and already consumed business events.
Follow-up 3. What single control would have reduced impact?
Answer: blocking analytics consumption on any CDC apply error. Treating row-level failures as authority-breaking events would have forced immediate containment instead of silent divergence.
Pro insider tip.
If writes succeed in the source but fail in the target, your warehouse is no longer a replica. It is an opinionated subset pretending to be truth.
Real-world incident during source to Redshift migration 19. Writes succeed in Redshift but fail in source.
During an AWS Redshift migration, certain application or pipeline writes were allowed to succeed directly in Redshift, while corresponding transactions failed or were rejected in the source system. As a result, Redshift advanced business state that never existed in the system of record, permanently inverting authority. Failure class: dual write inconsistency incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system writes enabled but intermittently failing or rejecting transactions. 2. Redshift cluster accepting direct or derived writes successfully. 3. CDC pipeline running or partially bypassed for some write paths. 4. Write path applications or jobs writing to Redshift even when source commits failed. 5. BI tools reading from Redshift and publishing analytics. 6. Declared source of truth, implicitly Redshift for analytics. 7. Authority status, inverted target advanced beyond source. Once the target advances independently, authority inversion occurs.
Incident analysis and root cause.
This incident resulted from a broken write hierarchy. 1. Triggering action allowing Redshift writes to commit despite corresponding source write failures. 2. Why it appeared safe, Redshift accepted data successfully and downstream reports updated without errors. 3. What teams noticed first, analytics showing records that were missing from operational systems. 4. What teams did not notice, that Redshift had become a write authority rather than a replica. 5. How divergence accumulated, each failed source write paired with a successful Redshift write widened the gap. 6. Missing invariant, the source system must be the single authoritative writer for business state.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it creates a believable but false business reality. Redshift data appears complete and internally consistent, while the source silently contradicts it. Validation passes because checks occur only in the target. Detection latency is often high, discovered during audits or operational reconciliation.
What exactly broke? Consistency breakdown.
Authoritative and transactional consistency are broken. Redshift contains business facts that the source system never committed. If we roll back only data, this inconsistency remains because the source never recorded those events.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate 1. Did Redshift accept writes the source rejected? Yes, authority inverted. 2. Do corresponding source records exist? No, events never committed. 3. Can Redshift-only writes be safely identified? Sometimes business dependent. 4. Have downstream systems consumed Redshift data? Likely trust already leaked. 5. Can authority be restored by snapshot alone? No, truth divergence permanent. Rollback cannot recreate events that never existed in the source.
Decision point, rollback versus forward fix.
Rollback is not meaningful because restoring snapshots only reproduces the same authority inversion. Forward fix must focus on reasserting source authority, invalidating Redshift-only state, and reconciling business impact explicitly.
Rollback architecture, if executed.
Rollback would require a full Redshift cluster snapshot restore to a pre-divergence point, followed by discarding all Redshift-only writes. CDC streams would need to be reset and reseeded from a verified source position. BI tools must be repointed back to the source, caches invalidated, and all downstream analytics rebuilt. Partial or table-level rollback is unsafe because phantom records are not domain isolated. Governance approval is mandatory due to the impact on published business decisions.
Code illustration and Redshift artifacts.
In this section, we will show 1. How Redshift contains records with no corresponding source commits. Detection is sufficient to prove irreversible authority inversion. Here is Redshift SQL showing records that exist only in the target system. Disclaimer: always test code in a non-production environment. This snippet proves that Redshift contains business records with no corresponding source commit. Their existence confirms inverted authority and makes clean rollback impossible.
Containment and forward fix strategy.
Once inverted authority is confirmed, containment must precede repair. 1. Immediately block all direct writes to Redshift. 2. Formally redeclare the source system as authoritative. 3. Invalidate analytics derived from Redshift-only records. 4. Manually reconcile business outcomes impacted by phantom data. 5. Re-enable analytics only after authority is restored. Authority must be restored before data can be trusted.
Interview framing, extremely important.
How would you explain this in an interview? 1. The target system accepted writes that the source rejected, inverting authority. 2. Redshift advanced business state that never existed in the system of record. 3. Rollback cannot restore truth because the source never committed those events. 4. Architectural principle: there must be exactly one authoritative write path. Authority inversion is permanent, not recoverable.
Follow-up 1. Why didn't monitoring catch this earlier?
Answer: monitoring focused on system health rather than semantic correctness. Redshift writes succeeded, pipelines stayed green, and no alerts fired to indicate that business truth had already diverged from the source.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe the moment Redshift-only records were consumed downstream. At that point, deleting them would invalidate decisions already made using that data.
Follow-up 3. What single rule would have prevented this?
Answer: enforcing a strict invariant that Redshift can never accept writes unless the source commit has succeeded and been acknowledged as authoritative.
Pro insider tip.
If Redshift ever contains data the source never committed, the migration has already failed, even if every dashboard is green.
Real-world incident. During source to Redshift migration 20, application retry logic creates duplicate records.
During an AWS Redshift migration, application-level retry logic reissued write operations after transient failures without a global idempotency guarantee. Some retries succeeded multiple times across systems, causing duplicate business records in Redshift while the source appeared consistent. Failure class: dual write inconsistency incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system write enabled with retries handled at application layer. 2. Redshift cluster accepting writes derived from application or CDC paths. 3. Retry mechanism enabled with at least once semantics and no idempotency key. 4. CDC pipeline running and applying changes without exactly once guarantees. 5. BI tools reading from Redshift and publishing metrics. 6. Declared source of truth assumed source for operations, Redshift for analytics. 7. Authority status split retries blurred write ownership. Retries without idempotency convert transient failures into permanent duplicates.
Incident analysis and root cause.
This incident emerged from retry amplification rather than a single failure. 1. Triggering action automatic retries reissued writes after timeouts or partial failures. 2. Why it appeared safe retries improved availability and masked transient errors. 3. What teams noticed first gradual inflation in counts and revenue metrics. 4. What teams did not notice the same logical event was applied multiple times. 5. How divergence accumulated. Each retry reapplied the same business intent. 6. Missing invariant exactly once apply with a globally enforced idempotency key.
Why this failure is dangerous, hidden risk.
This failure is dangerous because retries look like resilience. Systems remain healthy, latency improves, and no alarms fire. The corruption is semantic. Duplicates accumulate slowly and pass row count validation. Detection latency is often weeks, discovered during financial reconciliation.
What exactly broke? Consistency breakdown.
Transactional and domain-level consistency are broken. Multiple rows represent the same business event. If we roll back only data, this inconsistency remains because the system cannot deterministically distinguish original writes from retries.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate: 1. Are duplicates present in Redshift? Yes, semantic corruption. 2. Is a global idempotency key available? No ambiguous events. 3. Have downstream systems consumed inflated metrics, likely trust leaked? 4. Can duplicates be deterministically removed, sometimes business dependent? 5. Can authority be restored cleanly? No retry history lost. Rollback without event identity guarantees amplifies risk.
Decision point, rollback versus forward fix.
Rollback is rarely meaningful because removing duplicates requires business interpretation. Forward fix focuses on deduplication with auditability and enforcing idempotency before any reprocessing.
Rollback architecture, if executed.
A rollback would require restoring a preduplication snapshot and discarding all retry-applied data. CDC offsets would need to be discarded and reseeded from a verified boundary. BI tools must be repointed and caches invalidated. Partial rollback is unsafe because duplicates are interleaved across domains, requiring governance approval before execution.
Code illustration and Redshift artifacts.
In this section, we will show: 1. How duplicate business events are detected using business keys. Minimal proof is sufficient to demonstrate retry amplification. Here is Redshift SQL, detecting duplicate application caused by retries. Disclaimer: always test code in a non-production environment. This query proves that the same business identifier was applied multiple times. Without an idempotency key, the system cannot know which row represents the true event.
Containment and forward fix strategy.
Once retry amplification is confirmed, containment must precede repair. 1. Pause retry mechanisms that write to Redshift. 2. Declare a temporary trust freeze on affected metrics. 3. Deduplicate using audited business rules and checkpoints. 4. Introduce idempotency keys enforced at write boundaries. 5. Re-enable pipelines only after exactly once semantics are enforced. Retries without identity guarantees are data corruption.
Interview framing, extremely important.
How would you explain this in an interview? 1. Retries improved availability but violated exactly once guarantees. 2. The same business intent was applied multiple times. 3. Rollback is unsafe without deterministic event identity. 4. Architectural principle: idempotency must be enforced at the system boundary. Resilience without idempotency is corruption.
Follow-up 1. Why do retries cause duplicates only sometimes?
Answer: because retries occur under partial failures. Some attempts succeed before timeouts, others after. Without a shared idempotency key, each success is treated as a new event.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once duplicated events were consumed downstream. At that point, removing rows would invalidate business decisions already made.
Follow-up 3. What single control prevents this class of failure?
Answer: a globally enforced idempotency key that guarantees exactly once application across retries and systems.
Pro insider tip.
If your retry logic does not carry a stable idempotency key, you are not retrying safely. You are reapplying business intent.
Real-world incident during source to Redshift migration 21. Partial transaction replication breaks atomicity.
During an AWS Redshift migration, multi-statement transactions in the source system were partially replicated into Redshift. Some statements committed successfully while others were missing, resulting in logically impossible states where transactions appeared half-applied. Failure class: dual write inconsistency incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was: 1. Source system writes enabled with multi-statement transactions. 2. Redshift cluster accepting replicated writes derived from CDC or dual write logic. 3. Transaction handling no end-to-end transaction boundary enforced across systems. 4. CDC pipeline applying statements independently without atomic grouping. 5. BI tools reading from Redshift and publishing derived metrics. 6. Declared source of truth implicitly split between source and Redshift. 7. Authority status, assumed consistency without transactional guarantees. Atomicity cannot be reconstructed once transaction boundaries are lost.
Incident analysis and root cause.
This failure originated upstream and propagated silently. 1. Triggering action, replicating or dual-writing transactional changes statement by statement. 2. Why it appeared safe, individual statements applied successfully with no errors. 3. What teams noticed first, impossible intermediate states and analytical results. 4. What teams did not notice, that transactions were no longer atomic across systems. 5. How divergence accumulated. Each partial commit permanently altered target state. 6. Missing invariant, all-or-nothing transaction atomicity across replication boundaries.
Why this failure is dangerous, hidden risk.
This failure is dangerous because nothing is operationally broken. Pipelines remain green, lag appears normal, and row counts grow steadily. The corruption is logical. Redshift contains states that never existed in the source. Detection latency is often weeks, discovered only during deep business reconciliation.
What exactly broke? Consistency breakdown.
Transactional consistency is broken. Redshift reflects partial effects of transactions that should have been atomic. If we roll back only data, this inconsistency remains because the original transaction boundaries no longer exist in any system.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Were partial transactions applied in Redshift? Yes, atomicity broken. 2. Can original transaction boundaries be reconstructed? No, lost upstream. 3. Would Snapshot restore recover atomic state? No, corruption already present. 4. Have downstream systems consumed inconsistent data? Likely trust impacted. 5. Can authority be restored cleanly? No, transaction intent unrecoverable. Rollback cannot reassemble transactions that never arrived intact.
Decision point, rollback versus forward fix.
Rollback is not meaningful because restoring snapshots reproduces the same partial states. Forward fix must focus on acknowledging inconsistency, correcting downstream logic, and preventing recurrence rather than attempting reversal.
Rollback architecture, if considered.
A theoretical rollback would require full cluster snapshot restore, CDC offset discard, BI repointing, cache invalidation, and downstream data invalidation. However, because transaction atomicity was violated upstream, rollback only recreates corrupted state. Governance approval is required to formally declare rollback ineffective.
Code illustration and Redshift artifacts.
In this section, we will show 1. How partial transaction effects can be detected using relational inconsistencies. Minimal detection is sufficient to prove atomicity loss. Here is Redshift SQL, exposing partial transaction effects across related tables. Disclaimer: always test code in a non-production environment. This query detects parent records without corresponding child records, proving that a multi-table transaction was only partially applied in Redshift.
Containment and forward fix strategy.
Once partial transaction replication is confirmed, containment must precede repair. 1. Declare Redshift non-authoritative for affected domains. 2. Identify and flag logically impossible states. 3. Correct downstream metrics with explicit exclusions or compensations. 4. Redesign replication to enforce transactional grouping. 5. Revalidate migration only after atomicity invariants are enforced. You cannot fix atomicity after the fact.
Interview framing, extremely important.
How would you explain this in an interview? 1. Transactions lost atomicity across system boundaries. 2. Redshift contained states that never existed in source. 3. Rollback was ineffective because intent was unrecoverable. 4. Architectural principle: transaction boundaries must be preserved end-to-end. Atomicity is not optional in distributed systems.
Follow-up 1. Why didn't replication fail when transactions were partial?
Answer: because each statement was valid in isolation. Replication tools apply statements, not intent. Without explicit transaction grouping, partial success looks healthy operationally.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once partial effects were consumed downstream. At that point, restoring snapshots only recreated logically invalid states.
Follow-up 3. What single control would have prevented this?
Answer: enforcing transaction boundary preservation. so that either all statements replicate together or null do.
Pro insider tip.
If your replication pipeline does not understand transactions, it will eventually invent states your business never created.
Real-world incident during source to Redshift migration 22. No global transaction identifier across systems.
During an AWS Redshift migration involving dual write or CDC-based replication, the source system in Redshift operated without a shared global transaction identifier. As a result, writes that logically belong to the same business transaction could not be correlated across systems. This made it impossible to reason about completeness, ordering, or atomicity during validation or rollback. Failure class, dual write inconsistency incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system write enabled, generating transactions with local transaction IDs only. 2. Redshift cluster receiving replicated or dual-written changes without transaction correlation. 3. Replication mechanism CDC or application dual write without global transaction context. 4. Transaction visibility, each system tracked commits independently. 5. BI tools, reading from Redshift and assuming transactional completeness. 6. Declared source of truth, implicit and undocumented. 7. Authority status, assumed consistency without any shared transaction identity. Without a shared transaction identifier, systems cannot agree on what constitutes a single transaction.
Incident analysis and root cause.
This failure was architectural and unavoidable once the design choice was made. 1. Triggering action, designing replication or dual write without a global transaction identifier. 2. Why it appeared safe, individual tables and rows validated correctly in isolation. 3. What teams noticed first, inability to reconcile multi-table or multi-system inconsistencies. 4. What teams did not notice, that no mechanism existed to prove transactional completeness. 5. How divergence accumulated, independent commits created irreconcilable states over time. 6. Missing invariant, a globally unique transaction identifier spanning all systems.
Why this failure is dangerous, hidden risk.
This failure is dangerous because nothing appears broken. Data arrives, queries succeed, and metrics populate. The risk is epistemic. No one can ever prove whether a transaction fully succeeded or partially failed across systems. Detection latency is effectively infinite because the absence of proof is not detectable by monitoring.
What exactly broke? Consistency breakdown.
Transactional and referential consistency are fundamentally unprovable. There is no way to correlate writes across systems into a single business event. If we roll back only data, this inconsistency remains because transaction intent was never captured in a shared form.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Is there a global transaction identifier? No, correlation impossible. 2. Can partial transactions be detected deterministically? No, no linkage. 3. Would snapshot restore re-establish intent? No, intent never stored. 4. Have downstream systems consumed inconsistent state, likely undetectable impact? 5. Can authority be restored cleanly? No, truth cannot be reconstructed. Rollback without transaction identity restores data, not meaning.
Decision point, rollback versus forward fix.
Rollback is not meaningful because there is no way to prove correctness after restore. Forward fix must focus on architectural change, introducing a global transaction identifier, or redesigning workflows to tolerate eventual consistency with explicit boundaries.
Rollback architecture, if considered.
A theoretical rollback would involve full snapshot restore, CDC discard, BI repointing, cache invalidation, and downstream invalidation. However, without transaction identity, rollback cannot restore correctness or authority. Governance approval is required to formally declare rollback ineffective.
Containment and forward fix strategy.
Once the absence of transaction identity is acknowledged, containment must precede repair. 1. Declare transactional guarantees unsupported for the affected period. 2. Restrict analytics to single table or single domain scopes. 3. Communicate limitations explicitly to business stakeholders. 4. Introduce a global transaction identifier in the source or middleware. 5. Revalidate migration only after transaction correlation is possible. You cannot prove correctness without identity.
Interview framing, extremely important.
How would you explain this in an interview? 1. Transactions could not be correlated across systems. 2. Correctness could not be proven even when data looked complete. 3. Rollback failed because intent was never captured. 4. Architectural principle global transaction identity is required for provable consistency. Consistency is not just data movement, it is identity and intent.
Follow-up 1. Why can't SQL detect this problem?
Answer: SQL can validate rows and relationships, but it cannot infer intent. Without a transaction identifier, there is no way to know which rows belong together logically across systems.
Follow-up 2. When did rollback stop being viable?
Answer: rollback was never viable. From the moment writes occurred without global transaction identity, correctness became unprovable regardless of restore point.
Follow-up 3. What single design decision would have prevented this?
Answer: introducing a globally unique transaction identifier propagated end-to-end across source, replication, and target systems.
Pro insider tip.
If you cannot point to a single ID and say this is the transaction, you have already lost the ability to roll back with confidence.
Real-world incident during source to Redshift migration 23. Application-level retries amplify data divergence.
During an AWS Redshift migration using CDC and application-level retries, write operations that temporarily failed were retried by the application without idempotency guarantees. While some retries succeeded only on the source and others only on Redshift, the retry behavior amplified divergence silently. Over time, logically single business actions were applied multiple times across systems. Failure class, dual write inconsistency incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system write enabled with application-level retry logic on transient failures. 2. Redshift cluster receiving writes via CDC or dual write without idempotency enforcement. 3. Retry mechanism blind retries triggered on timeouts or partial failures. 4. Transaction correlation no shared retry or request identifier across systems. 5. BI tools reading from Redshift and assuming write once semantics. 6. Declared source of truth implicit and undocumented. 7. Authority status assumed consistency despite non-idempotent retries. Retries without idempotency multiply mistakes instead of fixing them.
Incident analysis and root cause.
This failure was caused by retry behavior interacting with migration state. 1. Triggering action retrying failed writes at the application layer during migration. 2. Why it appeared safe retries are normally used to improve reliability. 3. What teams noticed first gradual inflation of counts and aggregates in Redshift. 4. What teams did not notice that retries were reapplying already committed business actions. 5. How divergence accumulated, each retry created additional records without detection. 6. Missing invariant, exactly once application of business operations.
Why this failure is dangerous, hidden risk.
This failure is dangerous because retries are viewed as a safety feature. Systems remain operational, error rates drop, and dashboards look healthy. The damage is logical. The same intent is applied multiple times. Detection latency is typically weeks, discovered only during reconciliation or audit.
What exactly broke? Consistency breakdown.
Transactional and domain-level consistency are broken. Single business events exist multiple times with no reliable way to distinguish originals from retries. If we roll back only data, this inconsistency remains because intent duplication is indistinguishable from legitimate writes.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate 1. Were retries applied without idempotency keys? Yes, duplicates indistinguishable. 2. Can original versus retried writes be separated? No, same shape data. 3. Has Redshift accepted duplicated writes? Yes, amplified divergence. 4. Have downstream systems consumed inflated data? Likely trust impact. 5. Can authority be restored cleanly? No, intent ambiguity persists. Rollback cannot separate intent from repetition.
Decision point, rollback versus forward fix.
Rollback is not safe because restoring snapshots reproduces the same ambiguity. Forward fix must focus on declaring affected data unreliable, correcting aggregates, and redesigning retry logic to enforce idempotency before any future migration attempts.
Rollback architecture, if considered.
A theoretical rollback would involve full snapshot restore, CDC discard, BI repointing, cache invalidation, and downstream invalidation. However, without idempotency markers, rollback cannot restore correctness or authority. Governance approval is required to formally declare rollback ineffective.
Code illustration and Redshift artifacts.
In this section, we will show 1. How duplicate business keys reveal retry amplification. One proof of duplication is sufficient. Here is Redshift SQL showing duplicate business events caused by application retries. Disclaimer: always test code in a non-production environment. This snippet proves that the same business operation was applied multiple times. Without idempotency keys, these duplicates are indistinguishable from legitimate orders, making rollback unsafe.
Containment and forward fix strategy.
Once retry amplification is confirmed, containment must precede repair. 1. Immediately pause retry-enabled write paths. 2. Declare affected metrics unreliable for the impacted window. 3. Reconcile duplicates using external business context where possible. 4. Introduce idempotency keys at the application boundary. 5. Revalidate migration only after exactly once semantics are enforced. Retries without idempotency turn transient errors into permanent corruption.
Interview framing, extremely important.
How would you explain this in an interview? 1. Retries amplified divergence instead of fixing failures. 2. Exactly once semantics were assumed but never enforced. 3. Rollback failed because intent duplication cannot be reversed. 4. Architectural principle: retries must always be idempotent across systems. Reliability without idempotency is a data integrity risk.
Follow-up 1. Why are retries especially dangerous during migration?
Answer: during migration, writes may partially succeed across systems. Retries assume failure and reapply intent, but without shared idempotency keys, each retry becomes a new logical event. This silently multiplies divergence instead of correcting it.
Follow-up 2. When did rollback stop being safe here?
Answer: rollback stopped being safe the moment retries created indistinguishable duplicates. Once intent could no longer be separated from repetition, no snapshot or replay could restore correctness.
Follow-up 3. What single control would have prevented this?
Answer: end-to-end idempotency using a stable request or transaction identifier. With idempotency enforced, retries collapse into a single effect instead of amplifying corruption.
Pro insider tip.
If retries are enabled and idempotency is not enforced, every transient error is a potential data corruption event.
Real-world incident during source to Redshift migration 24. Business logic diverges between systems.
During an AWS Redshift migration, business logic embedded in the source system and downstream applications continue to evolve independently from the logic used to populate and interpret data in Redshift. Over time, calculations, filters, and conditional rules produced different business meanings from identical-looking data. This created a semantic split brain where data was structurally correct but logically inconsistent. Failure class: dual write inconsistency incident.
System state before failure, very important.
At the moment semantic divergence was introduced, the system state was 1. Source system write enabled with evolving business rules embedded in application logic. 2. Redshift cluster receiving data via CDC with static transformation and aggregation logic. 3. Business logic ownership split between application teams and analytics teams. 4. Validation focus structural checks only row count schema alignment. 5. BI tools reading from Redshift and assuming semantic equivalence. 6. Declared source of truth implicitly Redshift for analytics, source for operations. 7. Authority status semantically ambiguous and undocumented. Data can be identical while meaning is already different.
Incident analysis and root cause.
This failure emerged from ungoverned logic evolution. 1. Triggering action: business rules were modified in the source application without corresponding updates in Redshift transformations. 2. Why it appeared safe: data pipelines continued running and validations passed. 3. What teams noticed first: KPIs and metrics disagreed between operational dashboards and analytical reports. 4. What teams did not notice? That the disagreement stemmed from logic differences, not data defects. 5. How divergence accumulated. Each incremental logic change widened semantic mismatch. 6. Missing invariant, single authoritative definition of business logic.
Why this failure is dangerous, hidden risk.
This failure is dangerous because no system is technically broken. Queries succeed, pipelines are green, and data reconcile structurally. The corruption is semantic. Numbers mean different things in different contexts. Detection latency is often months, discovered only during audits, strategic reviews, or executive escalation.
What exactly broke? Consistency breakdown.
Domain level and semantic consistency are broken. The same rows represent different business truths depending on where they are interpreted. If we roll back only data, this inconsistency remains because logic divergence is not stored in data snapshots.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Are business rules identical across systems? No semantic drift exists. 2. Can historical logic versions be reconstructed? Rarely logic not versioned. 3. Would snapshot restore align meaning? No, logic remains divergent. 4. Have business decisions relied on Redshift semantics? Likely trust fractured. 5. Can authority be restored cleanly? No, meaning already split. Rollback restores data, not meaning.
Decision point, rollback versus forward fix.
Rollback is not meaningful because restoring any snapshot reproduces the same semantic ambiguity. Forward fix must focus on reconciling and governing business logic definitions rather than attempting data-level correction.
Rollback architecture, if considered.
A rollback would involve full snapshot restore, CDC discard, BI repointing, cache invalidation, and downstream invalidation. However, because business logic divergence is external to data state, rollback cannot restore correctness or authority. Governance approval is required to formally declare rollback ineffective.
Containment and forward fix strategy.
Once semantic divergence is confirmed, containment must precede repair. 1. Pause use of disputed metrics across the organization. 2. Declare a temporary canonical definition for each affected KPI. 3. Audit and document business logic differences explicitly. 4. Align application and analytics logic through shared specifications. 5. Revalidate historical reports under unified logic before restoring trust. Correct data with wrong meaning is more dangerous than missing data.
Interview framing, extremely important.
How would you explain this in an interview? 1. The data was structurally correct but semantically inconsistent. 2. Logic divergence occurred because definitions were not governed centrally. 3. Rollback failed because meaning cannot be recovered from data alone. 4. Architectural principle, business logic must have a single authoritative definition. Semantic drift is invisible to SQL but fatal to trust.
Follow-up 1. Why can't SQL prove this failure?
Answer: SQL validates structure and values, not intent or meaning. Two systems can return correct-looking numbers that represent different business definitions, and no query can detect that mismatch.
Follow-up 2. When did rollback stop being safe here?
Answer: rollback stopped being safe the moment business decisions relied on Redshift metrics derived from different logic. Once meaning diverges, restoring data cannot restore trust.
Follow-up 3. What single control would have prevented this?
Answer: versioned, centrally governed business logic shared across application and analytics layers. Without that, semantic drift is inevitable during migration.
Pro insider tip.
If two teams can explain the same metric differently, your migration failed long before the data did.
Category 3 wrap-up. Why dual-write failures are often permanent.
Dual-write inconsistency incidents demonstrate the most dangerous class of migration failures. Once business intent is applied differently across systems, no amount of replay, rollback, or reconciliation can reliably restore correctness. These failures permanently fracture authority because the same logical action produces different realities. The lesson from this category is simple. When systems disagree on what happened, trust cannot be rebuilt with data operations alone.
Transition from split authority to broken time.
While dual-write incidents break correctness across systems, The next category focuses on a more subtle and equally destructive failure mode. Even with a single writer and a single target, migrations can still fail when time itself is misinterpreted. Ordering, lateness, and temporal assumptions introduce corruption that often survives rollback intact.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs in a single zip file, containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, system design. Required for your data engineer interviews jobs like data quality analyst jobs, data governance analyst jobs, AWS Python data engineer jobs, AWS Redshift database administrator DBA jobs, AWS Glue ETL developer jobs, AWS data engineer jobs, cloud data engineer jobs, data architect jobs, DataOps engineer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem-solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Category 4. Temporal Consistency Incidents.
Temporal consistency incidents occur when data is correct in isolation, but incorrect in sequence. Events arrive late, backfills overwrite newer facts, timestamps are misinterpreted, or clocks disagree. These failures are especially dangerous because rollback restores data state but not time semantics. Once ordering is wrong, historical truth becomes ambiguous.
Category 4 Scenarios. Temporal Consistency Failures.
The following scenarios illustrate how time-based assumptions break during migration. 1. Late arriving data applied after cutover, rewriting closed business periods. 2. Backfill operations overriding newer CDC applied data. 3. Event time versus processing time mismatches producing incorrect aggregations. 4. Time zone conversion differences between source, ingestion, and analytics layers. 5. Clock skew between source systems and ingestion nodes altering event order. 6. Slowly changing dimensions applied out of sequence, corrupting history. 7. Aggregates drifting over time due to cumulative temporal misalignment. Core failure, ordering, and time semantics break.
Real-world incident during source to Redshift migration 25. Late arriving data applied after authority cutover.
During an AWS Redshift migration, Redshift was formally declared the authoritative analytics system after cutover. However, delayed CDC events from the source system continued to arrive and were applied to Redshift after this authority switch. These late-arriving records altered historical metrics post-cutover, silently corrupting time-based analytics. Failure class, temporal consistency incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system write-enabled prior to cutover, then logically deprecated for analytics. 2. Redshift cluster declared authoritative for analytics after cutover timestamp. 3. CDC pipeline still running with lag delivering delayed events. 4. CDC offset position behind real-time at cutover moment. 5. BI tools fully pointed to Redshift and publishing results. 6. Declared source of truth Redshift post-cutover. 7. Authority status explicitly switched but not enforced against late data. Authority was declared but temporal enforcement was missing.
Incident analysis and root cause.
This failure resulted from a broken temporal assumption. 1. Triggering action declaring Redshift authoritative while CDC was still catching up. 2. Why it appeared safe, CDC lag was considered acceptable and shrinking. 3. What teams noticed first? Historical KPIs changed after cutover without explanation. 4. What teams did not notice that late-arriving events were mutating closed reporting periods. 5. How divergence accumulated. Each delayed event rewrote historical truth post-authority switch. 6. Missing invariant. No data with event time earlier than cutover may be applied after authority switch.
Why this failure is dangerous, hidden risk.
This failure is dangerous because systems appear healthy. CDC runs successfully, row counts grow as expected, and dashboards refresh normally. The corruption is semantic and temporal, historical truth changes after decisions are made. Detection latency is often days or weeks, discovered only when reports no longer reconcile.
What exactly broke? Consistency breakdown.
Temporal consistency is broken. The timeline of business events is no longer stable after cutover. Redshift cannot represent a single point-in-time truth. If we roll back only data, this inconsistency remains because late events will be reapplied unless temporal authority rules change.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Was Redshift declared authoritative before CDC fully caught up? Yes, temporal risk. 2. Have late-arriving events already been applied? Yes, history mutated. 3. Can late events be cleanly separated from valid history, sometimes event time dependent? 4. Have downstream systems consumed post-cutover metrics? Likely. 5. Can authority be restored without freezing time semantics? No, semantics already shifted. Rollback restores state, not historical meaning.
Decision point, rollback versus forward fix.
Rollback is rarely effective because restoring snapshots reintroduces the same late-arriving events unless CDC rules change. Forward fix is preferred, focusing on enforcing temporal cutoffs and correcting downstream expectations.
Rollback architecture, if executed.
Rollback would require restoring a snapshot taken at cutover, discarding all post-cutover CDC data, and permanently blocking late-arriving events. CDC offsets must be receded to a strict post-cutover boundary. BI caches must be invalidated, downstream reports marked obsolete, and governance approval obtained. Partial rollback is forbidden because reintroducing mixed timelines worsens inconsistency.
Code illustration and Redshift artifacts.
In this section, we will show 1. How late-arriving events are detected relative to cutover time. Temporal proof, not volume, exposes this failure. Detection logic, identifying post-cut over historical mutation. Disclaimer, always test code in a non-production environment. This detection query identifies temporal ghosts. It proves that events belonging to a pre-cutover timeline were ingested after authority switched, confirming a breach of the temporal consistency invariant.
Containment and forward fix strategy.
Once late-arriving data is confirmed, containment must precede repair. 1. Freeze historical partitions immediately. 2. Declare an immutable cutover timestamp for analytics. 3. Quarantine late-arriving records for manual review. 4. Recompute affected aggregates with explicit time boundaries. 5. Enforce event time validation in CDC before re-enabling ingestion. Time must be governed, not assumed.
Interview framing, extremely important.
1. Explain that authority without temporal enforcement is meaningless. 2. Highlight that CDC lag is acceptable only before authority declaration. 3. State that rollback cannot fix semantic time corruption. 4. Architectural principle, time invariance must be enforced at system boundaries.
Follow-up 1. Why don't row counts detect this issue?
Answer, row counts increase normally because late data is still valid data structurally. The failure is about when data is applied, not whether it exists. Validation that ignores time semantics provides false confidence.
Follow-up 2. When did rollback stop being safe?
Answer, rollback stopped being safe the moment late-arriving events were applied after authority declaration. From that point on, historical truth had already changed for consumers.
Follow-up 3. What single control would have prevented this?
Answer, a hard event time cutoff enforced at CDC ingestion. Authority switches must be accompanied by temporal guards, not just routing changes.
Pro insider tip.
If historical numbers change after cutover without a code deploy, assume late-arriving data, breached your authority boundary.
Real-world incident during source to Redshift migration 26. Backfill overwrites newer CDC data.
During an AWS Redshift migration, a historical backfill job was executed after CDC had already begun applying newer changes. The backfill did not respect event time or version ordering and overwrote more recent CDC-applied data with older values. This silently reverted business state and corrupted time-based correctness. Failure class, temporal consistency incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system write-enabled and producing continuous changes. 2. Redshift cluster actively receiving CDC-applied incremental updates. 3. CDC pipeline running and mostly caught up with source head. 4. Backfill process manually triggered to correct historical gaps. 5. BI tools fully pointed to Redshift and publishing analytics. 6. Declared source of truth. Redshift for analytics. 7. Authority status declared but not protected against retroactive rights. Backfill without temporal guards can rewrite the present with the past.
Incident analysis and root cause.
This failure resulted from violating a fundamental ordering rule. 1. Triggering action, running a bulk backfill job after CDC had already applied newer changes. 2. Why it appeared safe, backfill was assumed to affect only historical periods. 3. What teams noticed first, recently corrected values reverted unexpectedly in reports. 4. What teams did not notice, that backfill jobs were not constrained by event time or version checks. 5. How divergence accumulated. Each backfill execution overwrote newer CDC state with older snapshots. 6. Missing invariant. Older data must never overwrite newer state once CDC is authoritative.
Why this failure is dangerous, hidden risk.
This failure is dangerous because pipelines remain green and data volumes appear correct. The corruption is logical. Newer truth is silently replaced by older values. Detection latency is often long, surfacing only when users compare reports across time or rerun reconciliations.
What exactly broke? Consistency breakdown.
Temporal and transactional consistency are broken. The ordering of updates is reversed, violating last write wins assumptions. Redshift no longer reflects the true sequence of business events. If we roll back only data, this inconsistency remains because the same backfill process will overwrite newer data again unless constrained.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Has newer CDC data already been overwritten? Yes, state regression occurred. 2. Can overwritten values be reconstructed from source logs, sometimes log-dependent? 3. Is the backfill job idempotent and order-aware? No, root cause persists. 4. Have downstream systems consumed regressed data? Likely. 5. Can authority be restored without enforcing ordering constraints? No. Rollback without fixing ordering rules recreates the same failure.
Decision point, rollback versus forward fix.
Rollback is risky because restoring a snapshot does not prevent the backfill process from reintroducing the same corruption. Forward fix is preferred, focusing on enforcing strict ordering constraints and correcting affected downstream outputs.
Rollback architecture, if executed.
Rollback would require restoring a snapshot taken before the backfill execution, discarding all data written by the backfill job, and disabling all backfill processes. CDC offsets must be preserved, BI caches invalidated, and downstream consumers notified. Rollback is only viable if the backfill job is permanently constrained or removed before reingestion.
Code illustration and Redshift artifacts.
In this section, we will show 1. How newer CDC data was overwritten by older backfill values. Ordering violations require proof, not volume checks. Here is Redshift SQL showing older backfill data, overriding newer CDC state. Disclaimer: always test code in a non-production environment. This snippet proves that records with older event time values were ingested after newer CDC updates, confirming that historical backfill overwrote more recent state.
Containment and forward fix strategy.
Once overwrite is confirmed, containment must precede repair. 1. Immediately disable all backfill jobs. 2. Declare CDC as the sole writer for affected tables. 3. Reconstruct correct state using source of truth ordering. 4. Recompute downstream aggregates explicitly. 5. Introduce event time or version guards on all future backfills. Backfill must obey time, not convenience.
Interview framing, extremely important.
1. Explain that backfill is a write, not a read-only operation. 2. Highlight that CDC authority must block retroactive writes. 3. State that rollback fails if ordering rules remain broken. 4. Architectural principle time ordering must be enforced at ingestion boundaries.
Follow-up 1. Why didn't validation catch this immediately?
Answer: row counts and freshness checks still pass because data volume and timestamps look reasonable. The failure is about order, not presence. Without explicit ordering validation, corruption remains invisible.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once overwritten values were consumed downstream. At that point, restoring snapshots without fixing the backfill process would recreate the same regression.
Follow-up 3. What single guard would have prevented this?
Answer: a strict rule that backfill jobs cannot write rows newer than the current CDC watermark. Enforcing this invariant prevents historical data from overriding present state.
Pro insider tip.
If a backfill can overwrite CDC data, you do not have a pipeline. You have competing writers with no clock.
Real-world incident during source to Redshift migration 27. Event time versus processing time mismatch corrupts temporal truth.
During an AWS Redshift migration, analytics were validated using ingestion timestamps instead of business event timestamps. CDC delivered records out of real-world order, but dashboards relied on processing time as a proxy for truth. This caused reports to reflect when data arrived, not when business events actually occurred, silently corrupting time-based analytics. Failure class: temporal consistency incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system write-enabled and emitting business events with explicit event time. 2. Redshift cluster receiving CDC events with ingestion timestamps. 3. CDC pipeline running and delivering events asynchronously. 4. Timestamp usage, analytics relying on ingestion_time instead of event_time. 5. BI tools, fully pointed to Redshift and publishing time series reports. 6. Declared source of truth, Redshift for analytics. 7. Authority status declared but temporal semantics not enforced. Time semantics were assumed, not governed.
Incident analysis and root cause.
This failure resulted from a semantic mismatch in time interpretation. 1. Triggering action using processing time as the primary timeline for analytics after cutover. 2. Why it appeared safe, data arrived continuously and dashboards updated without gaps. 3. What teams noticed first, metrics appeared to spike or dip at unexpected times. 4. What teams did not notice, that late or retried events were shifting business activity across reporting windows. 5. How divergence accumulated, each delayed event was counted in the wrong time bucket. 6. Missing invariant, business analytics must be ordered by event time, not ingestion time.
Why this failure is dangerous, hidden risk.
This failure is dangerous because nothing looks broken operationally. CDC is healthy, data volumes are correct, and dashboards refresh normally. The corruption is semantic. The timeline no longer reflects reality. Detection latency is often weeks, discovered only when reports are reconciled against operational logs.
What exactly broke? Consistency breakdown.
Temporal consistency is broken. The ordering of events reflects processing delays rather than real-world occurrence. Redshift cannot answer questions about when things actually happened. If we roll back only data, this inconsistency remains because the same processing time logic will reapply.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate 1. Were analytics already built on processing time semantics? Yes, meaning already shifted. 2. Can historical event time be reconstructed reliably, sometimes source-dependent? 3. Have downstream systems consumed time-shifted metrics? Likely. 4. Would snapshot restore change time interpretation? No, logic unchanged. 5. Can authority be restored without redefining time semantics? No. Rollback restores rows, not meaning.
Decision point, rollback versus forward fix.
Rollback is ineffective because restoring earlier snapshots does not change how time is interpreted. Forward fix is required. focusing on redefining analytics to use event time consistently and correcting downstream expectations.
Rollback architecture, if executed.
Rollback would involve restoring a snapshot taken before analytics adoption, invalidating all time-based reports, and repointing BI tools back to the source or a quarantined dataset. CDC offsets may be preserved, but rollback alone does not fix the failure unless time semantics are redesigned. Governance approval is required to invalidate previously published metrics.
Code illustration and Redshift artifacts.
In this section, we will show 1. How event time and ingestion time diverge for the same records. One comparison is enough to expose semantic drift. Here is Redshift SQL showing mismatch between event time and processing time. Disclaimer: always test code in a non-production environment. This snippet proves that business events are being counted on a different day than when they actually occurred. This confirms semantic time drift rather than data loss.
Containment and forward fix strategy.
Once time mismatch is confirmed, containment must precede repair. 1. Freeze publication of time-based KPIs. 2. Declare event time as the only valid analytical timeline. 3. Rebuild aggregates using event time semantics. 4. Backfill corrected timelines explicitly. 5. Redesign CDC ingestion to preserve and enforce event time ordering. Time must be defined once and enforced everywhere.
Interview framing, extremely important.
1. Explain the difference between event time and processing time clearly. 2. State that using ingestion time rewrites business history. 3. Highlight that rollback cannot fix semantic time errors. 4. Architectural principle: business truth must be ordered by event time.
Follow-up 1. Why do dashboards look healthy in this scenario?
Answer: because data volume and freshness appear normal. The system is operationally healthy, but analytically wrong. Processing time hides the fact that events are attributed to incorrect periods.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once time-based decisions were made using processing time metrics. At that point, restoring earlier data does not undo the semantic shift in interpretation.
Follow-up 3. What single design rule prevents this class of failure?
Answer: mandating that all analytical logic uses event time as the primary key for ordering and aggregation. Processing time should never define business truth.
Pro insider tip.
If your revenue graph changes when ingestion slows down, you are charting your pipeline, not your business.
Real-world incident during source to Redshift migration 28. Time zone conversion differences corrupt temporal semantics.
During an AWS Redshift migration, timestamps were ingested from the source system and interpreted using a different time zone assumption in Redshift. While raw values appeared correct and row counts matched, business events were shifted in time, causing reports to disagree on daily, hourly, and cutoff-based metrics. Rollback did not restore correctness because the semantic meaning of time had already diverged. Failure class: temporal consistency incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system write-enabled, storing timestamps with implicit or explicit time zone semantics. 2. Redshift cluster loaded data interpreting timestamps using a different session or column time zone. 3. CDC pipeline actively replicating timestamp fields without normalization. 4. BI tools pointed to Redshift for analytics and daily reporting. 5. Declared source of truth: Redshift for analytics post-cutover. 6. Authority status declared without validating time semantics equivalence. Temporal authority depends on meaning, not just values.
Incident analysis and root cause.
This failure was caused by a semantic mismatch in time interpretation. 1. Triggering action: loading timestamps into Redshift without enforcing a consistent time zone normalization strategy. 2. Why it appeared safe: raw timestamp values matched visually and row counts validated successfully. 3. What teams noticed first: daily and hourly reports disagreed between legacy dashboards and Redshift. 4. What teams did not notice: that the same instant in time was represented differently across systems. 5. How divergence accumulated: aggregations and cutoffs were computed against shifted timelines. 6. Missing invariant, event time semantics must be preserved exactly across systems.
Why this failure is dangerous, hidden risk.
This failure is dangerous because all data appears present and structurally valid. Queries succeed, counts match, and no CDC errors occur. The corruption is semantic. Business events are assigned to the wrong day or hour. Detection latency is often weeks, discovered only during financial close, audits, or executive reconciliation.
What exactly broke? Consistency breakdown.
Temporal and domain-level consistency are broken. The same business event belongs to different reporting windows depending on the system. Redshift can no longer be trusted for time-based analytics. If we roll back only data, this inconsistency remains because the time zone interpretation error is embedded in how timestamps were consumed and reported.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Has Redshift accepted analytical usage? Yes, reports already consumed. 2. Are timestamps materially incorrect? Yes, semantic shift present. 3. Would snapshot restore fix interpretation? No, same semantics reapply. 4. Have downstream reports relied on shifted time windows? Likely. 5. Can authority be restored without re-education? No, meaning already fractured. Rollback restores data, not meaning.
Decision point, rollback versus forward fix.
Rollback is not effective because restoring snapshots reproduces the same time zone interpretation. Forward fix is required to normalize time semantics, reprocess affected metrics, and explicitly communicate corrected timelines to stakeholders.
Rollback architecture, if considered.
Rollback would require discarding Redshift analytics usage, restoring a pre-cutover snapshot, and freezing all reporting. However, because the same time zone assumptions would still apply, rollback does not restore correctness. CDC offsets would not change the semantic error, making rollback destructive without benefit.
Code illustration and Redshift artifacts.
In this section, we will show 1. How timestamp values differ when interpreted under different time zones. 2. How reporting windows shift despite identical raw values. Time zone errors hide in plain sight. Here is Redshift SQL showing time zone interpretation differences. Disclaimer: always test code in a non-production environment. This comparison proves that the same stored timestamp represents different instances depending on time zone interpretation, directly impacting daily and hourly aggregations.
Containment and forward fix strategy.
Once time zone drift is confirmed, containment must precede repair. 1. Freeze time-based reporting temporarily. 2. Declare the correct canonical time zone for all events. 3. Reprocess affected tables with explicit time zone normalization. 4. Rebuild aggregates and validate against source cutoffs. 5. Communicate corrected timelines to all consumers. Time must be normalized before it can be trusted.
Interview framing, extremely important.
How would you explain this in an interview? 1. Explain that timestamp equality does not guarantee temporal equivalence. 2. Highlight that time zone is part of data semantics, not presentation. 3. Emphasize that rollback cannot fix semantic interpretation errors. 4. State the architectural principle, preserve event time meaning across systems.
Follow-up 1. Why don't row counts detect this issue?
Answer: row counts only validate quantity, not temporal meaning. Every row is present, but events are assigned to incorrect reporting windows. This causes KPI drift without triggering validation failures.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once reports were generated and decisions were made using shifted time windows. At that point, restoring snapshots would not undo the semantic damage.
Follow-up 3. What single control would have prevented this?
Answer: enforcing a strict rule that all timestamps must be normalized to a canonical time zone at ingestion. Time zone handling must be treated as a data contract, not a BI concern.
Pro insider tip.
If you do not explicitly normalize time at ingestion, your warehouse will faithfully answer the wrong questions forever.
Real-world incident during source to Redshift migration 29. Clock skew between source and ingestion nodes.
During an AWS Redshift migration, the source database servers and ingestion nodes, DMS, glue, or custom CDC workers, were not time synchronized. As a result, event timestamps and ingestion timestamps drifted relative to each other. CDC applied changes in an order that appeared valid operationally but was temporally incorrect, corrupting time-based analytics. Rollback could not restore correctness because the underlying time reference was inconsistent. Failure class, temporal consistency incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system write enabled using local system clock for transaction timestamps. 2. Ingestion nodes running on separate hosts with unsynchronized system clocks. 3. Redshift cluster receiving CDC applied events ordered by ingestion time. 4. CDC pipeline running continuously without clock drift detection. 5. BI tools pointed to Redshift for time-based analytics. 6. Declared source of truth, Redshift after cutover. 7. Authority status declared without validating time synchronization guarantees. Time authority depends on synchronized clocks, not ingestion success.
Incident analysis and root cause.
This failure originated from an infrastructure-level assumption. 1. Triggering action, running CDC ingestion on nodes without enforcing strict NTP synchronization. 2. Why it appeared safe, CDC lag was low and no replication errors were reported. 3. What teams noticed first, events appearing out of expected chronological order in reports. 4. What teams did not notice, that ingestion time and event time were diverging subtly. 5. How divergence accumulated, ordering logic relied on skewed clocks, compounding misordering over time. 6. Missing invariant, all systems participating in CDC must share a consistent and synchronized time reference.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it produces plausible but incorrect timelines. Data loads successfully, validations pass, and no alarms fire. The corruption is temporal. Events are assigned the wrong relative order. Detection latency is often weeks, surfacing only when sequence-dependent analytics or audits fail.
What exactly broke? Consistency breakdown.
Temporal consistency is broken. The same sequence of business events is ordered differently depending on which clock was used. Redshift becomes untrustworthy for any time-ordered analysis. If we roll back only data, this inconsistency remains because the original event ordering was derived from skewed clocks.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate 1. Were source and ingestion clocks synchronized? No, ordering corrupted. 2. Can true event order be reconstructed? No, time reference unreliable. 3. Would snapshot restore fix ordering? No, same skew reapplies. 4. Have downstream systems consumed misordered data? Likely. 5. Can authority be restored without redefining time semantics? No. Rollback cannot restore an ordering that never existed.
Decision point, rollback versus forward fix.
Rollback is ineffective because restoring snapshots preserves the same skewed ordering assumptions. Forward fix must focus on enforcing time synchronization, redefining ordering rules, and rebuilding affected analytics with corrected temporal semantics.
Rollback architecture, if considered.
Rollback would require discarding all time-ordered analytics, restoring a pre-cutover snapshot, and freezing reporting. However, without correcting clock synchronization first, rollback reproduces the same failure. CDC offsets and snapshots cannot compensate for invalid time foundations.
Containment and forward fix strategy.
Once clock skew is confirmed, containment must precede repair. 1. Freeze sequence and time-dependent analytics immediately. 2. Enforce strict NTP synchronization across all source and ingestion hosts. 3. Redefine ordering logic to rely on source commit sequence where possible. 4. Reprocess affected data after time synchronization is verified. 5. Revalidate all time-based reports before restoring trust. You cannot reason about time on an unsynchronized system.
Interview framing, extremely important.
How would you explain this in an interview? 1. Low CDC lag does not guarantee correct event ordering. 2. Clock synchronization is a data correctness dependency, not an ops detail. 3. Rollback cannot fix ordering derived from invalid time sources. 4. Architectural principle, time must be globally consistent before it can be authoritative.
Follow-up 1. Why doesn't CDC detect clock skew?
Answer: CDC assumes timestamps and ordering are meaningful inputs. As long as changes can be applied, the pipeline remains healthy. The failure is semantic, not operational, so no error is raised.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once misordered events were consumed by downstream analytics. At that point, restoring snapshots could not reconstruct the correct sequence of events.
Follow-up 3. What single control would have prevented this?
Answer: mandatory NTP enforcement and monitoring on all systems participating in CDC. Time synchronization must be treated as a hard prerequisite for any migration activity.
Pro insider tip.
If you do not trust your clocks, you cannot trust your data ordering, and no amount of SQL will fix that.
Real-world incident during source to Redshift migration 30. Slowly changing dimensions, misaligned after cutover.
During an AWS Redshift migration, dimension tables using SCD Type 2 logic were replicated via CDC while fact tables were validated independently. Due to timing differences, overlapping validity windows were introduced in Redshift. Although row counts and keys matched, historical joins produced incorrect results. Rollback could not restore correctness because business time semantics were already violated. Failure class: temporal consistency incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system, write enabled with SCD Type 2 logic enforcing non-overlapping validity windows. 2. Redshift cluster receiving CDC applied dimension changes independently of fact validation. 3. CDC pipeline running continuously without enforcing SCD temporal constraints. 4. Fact tables validated separately using row counts and aggregates. 5. BI tools pointed to Redshift for historical reporting. 6. Declared source of truth Redshift after cutover. 7. Authority status declared without revalidating temporal invariance. SCD correctness depends on time semantics, not row completeness.
Incident analysis and root cause.
This failure originated from a broken temporal assumption. 1. Triggering action, applying CDC changes to SCD dimension tables without enforcing non-overlapping effective date rules. 2. Why it appeared safe, dimension row counts and surrogate keys match the source. 3. What teams noticed first, historical reports showing inconsistent attribute values for the same business entity. 4. What teams did not notice, overlapping effective underscore from and effective underscore to ranges in Redshift. 5. How divergence accumulated. Each CDC update introduced new rows without closing prior validity windows correctly. 6. Missing invariant. SCD validity windows must be strictly non-overlapping and contiguous.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it passes most standard validations. Tables load successfully, counts match, and CDC runs cleanly. The corruption is semantic, historical truth becomes ambiguous. Detection latency is often weeks, surfacing only when users question conflicting historical attributes.
What exactly broke? Consistency breakdown.
Temporal and domain-level consistency are broken. The same business entity is valid in multiple states at the same point in time. Redshift becomes untrustworthy for historical joins. If we roll back only data, this inconsistency remains because the incorrect validity ranges are already materialized.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate 1. Are SCD validity windows overlapping in Redshift? Yes, semantic corruption. 2. Is the original business time logic recoverable automatically? No, rule-based. 3. Would snapshot restore fix window alignment? No, same CDC logic reapplies. 4. Have downstream reports consumed ambiguous history? Likely. 5. Can authority be restored without redefining SCD rules? No. Rollback restores rows, not business time semantics.
Decision point, rollback versus forward fix.
Rollback is ineffective because restoring snapshots reproduces the same misaligned validity logic. Forward fix must focus on redefining SCD rules, correcting validity windows, and reprocessing affected dimensions with explicit business approval.
Rollback architecture, if considered.
Rollback would require restoring a pre-cutover snapshot, discarding all CDC-applied SCD changes, and freezing analytics. However, without correcting the SCD enforcement logic first, rollback recreates the same overlap. Snapshot and CDC mechanics cannot infer business time rules.
Code illustration and Redshift artifacts.
In this section, we will show 1. How overlapping SCD validity windows are detected in Redshift. 2. Why this proves semantic corruption rather than data loss. Temporal overlap is the signature of SCD failure. Forensic audit, detecting SCD timeline corruption via window functions. Disclaimer, always test code in a non-production environment. This audit query identifies self-intersecting timelines. It proves that multiple rows are valid for the same key at the same time, violating the SCD Type 2 invariant and causing non-deterministic joins in downstream reports.
Containment and forward fix strategy.
Once SCD misalignment is confirmed, containment must precede repair. 1. Freeze historical reporting that relies on affected dimensions. 2. Define authoritative SCD rules with business stakeholders. 3. Correct validity windows using controlled auditable scripts. 4. Reprocess dependent fact joins after dimension repair. 5. Revalidate historical reports before restoring trust. SCD repair is a business decision before it is a technical one.
Interview framing, extremely important.
How would you explain this in an interview? 1. Row counts do not validate historical correctness for SCD dimensions. 2. CDC moves rows but does not enforce business time rules. 3. Rollback cannot fix invalid temporal semantics. 4. Architectural principle, business time invariance must be enforced explicitly during migration.
Follow-up 1. Why do standard validations miss SCD overlap?
Answer: standard validations focus on completeness, not time semantics. As long as rows exist and keys match, checks pass. Overlaps only surface when historical joins are evaluated.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once overlapping history was consumed by reports. At that point, restoring snapshots could not guarantee which version of history was correct.
Follow-up 3. What single control would have prevented this?
Answer: enforcing SCD validity constraints during CDC application. Migration pipelines must actively validate temporal rules, not assume the target enforces them.
Pro insider tip.
If your SCD tables validate only by row count, assume your historical truth is already broken.
Real-world incident during source to Redshift migration 31. Aggregates drift over time after cutover.
During an AWS Redshift migration, aggregate metrics initially matched between the source system and Redshift at cutover. Over time, however, the same aggregates began to drift despite no obvious data loss or pipeline failures. The underlying data remained mostly intact, but time-based accumulation semantics diverged, producing steadily worsening analytical discrepancies. Failure class, temporal consistency incident.
System state before failure, very important.
At the moment the failure pattern began, the system state was 1. Source system writes enabled, continuously accumulating transactional data. 2. Redshift cluster declared authoritative for analytics post-cutover. 3. CDC pipeline running continuously with acceptable lag. 4. Aggregation logic recomputed periodically in Redshift using time windows. 5. BI tools fully repointed to Redshift for trend and KPI reporting. 6. Declared source of truth, Redshift for all analytical metrics. 7. Authority status formally declared but temporal invariance not revalidated. Aggregate correctness depends on long-term temporal alignment, not point-in-time checks.
Incident analysis and root cause.
This failure emerged through slow, compounding divergence. 1. Triggering condition, relying on rolling aggregates in Redshift without revalidating long-term time semantics after cutover. 2. Why it appeared safe, initial aggregate values matched exactly during early validation windows. 3. What teams noticed first, trend lines and month-over-month metrics slowly diverged from legacy reports. 4. What teams did not notice, small timing differences accumulating with each aggregation cycle. 5. How divergence accumulated, minor late arrivals, window alignment differences, and reprocessing effects compounded over time. 6. Missing invariant, aggregation windows must be temporally equivalent across systems over the full life cycle.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it does not appear immediately. Early dashboards look correct, validations pass, and confidence grows. Over weeks or months, however, small discrepancies compound into materially incorrect trends. Detection latency is typically long and often attributed to business volatility rather than data error.
What exactly broke? Consistency breakdown.
Temporal and semantic consistency are broken. Aggregates no longer represent the same business reality over time. Redshift becomes untrustworthy for trend analysis, even though individual rows are largely correct. If we roll back only data, this inconsistency remains because the accumulated temporal interpretation has already diverged.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Did aggregates match only at initial cutover? Yes, drift appeared later. 2. Are discrepancies growing over time? Yes, compounding effect. 3. Would snapshot restore reset aggregate interpretation? No, drift will recur. 4. Have business decisions relied on long-term trends? Likely. 5. Can authority be restored without redefining aggregation logic? No. Rollback resets data, not accumulated meaning.
Decision point, rollback versus forward fix.
Rollback is ineffective because restoring snapshots reproduces the same aggregation behavior. Forward fix must focus on redefining temporal aggregation rules, aligning window semantics, and recalculating historical aggregates under a single authoritative model.
Rollback architecture, why rollback fails here.
Rollback in this scenario would require a full system reset, but it cannot restore analytical correctness. Restoring a Redshift snapshot would only reset raw data, not the accumulated temporal interpretation already consumed by the business. CDC rewind is ineffective because the same aggregation logic would reintroduce drift. BI cache invalidation does not undo decisions made from historical trends. Downstream consumers would still retain interpretations derived from drifting aggregates. Governance approval for rollback is typically denied because rollback recreates the same behavior rather than correcting it.
Code illustration and Redshift artifacts.
In this section, we will show 1. How rolling aggregates in Redshift drift compared to source over time. 2. Why this proves temporal accumulation mismatch rather than data loss. Trend divergence is the signature of temporal accumulation failure. Here is Redshift SQL showing rolling aggregate drift over time. Disclaimer: always test code in a non-production environment. This aggregate appears correct in isolation. Comparing this result month over month against the source exposes gradual divergence, proving that temporal accumulation semantics differ even when raw data looks intact.
Containment and forward fix strategy.
Once aggregate drift is confirmed, containment must precede repair. 1. Pause reliance on long-term trend metrics. 2. Declare aggregates provisional until revalidated. 3. Define authoritative aggregation windows and cutoffs. 4. Recompute historical aggregates under the corrected model. 5. Revalidate trends before restoring business trust. Trends amplify small errors into big decisions.
Interview framing, extremely important.
How would you explain this in an interview? 1. Point-in-time validation does not guarantee long-term analytical correctness. 2. Aggregates are sensitive to late data and window alignment. 3. Rollback cannot fix semantic drift once trends are consumed. 4. Architectural principle time semantics must be explicitly governed, not assumed.
Follow-up 1. Why do aggregates drift when row-level data looks correct?
Answer: aggregates amplify small timing differences. Late-arriving data, window alignment, or reprocessing effects compound over time. Each cycle looks reasonable, but the accumulated result diverges.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once business decisions relied on long-term trends. At that point, restoring raw data could not undo interpretations already made from drifting aggregates.
Follow-up 3. What single control would have reduced this risk?
Answer: continuous aggregate reconciliation over extended windows. Comparing trends over weeks or months would have exposed drift before trust fully shifted to Redshift.
Pro insider tip.
If your aggregates match today but drift next month, the problem is almost never the math, it is the timeline.
Category 4 wrap-up, when time corrupts truth.
Temporal consistency failures are dangerous because they often survive rollback. Even when data is restored successfully, time semantics remain broken. Ordering, effective dates, and aggregation windows silently drift, leaving analytics technically correct but historically wrong. These incidents teach that restoring state is not the same as restoring meaning.
Transition from time drift to validation illusions.
Temporal failures break correctness quietly. Validation blind spots are worse. They convince teams that everything is safe. In the next category, we examine failures where validation actively lies, creating false confidence during migration and pushing teams past rollback boundaries without realizing it.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs in a single zip file, containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, system design. Required for your data engineer interviews jobs like data quality analyst jobs, data governance analyst jobs, AWS Python data engineer jobs, AWS Redshift database administrator DBA jobs, AWS Glue ETL developer jobs, AWS data engineer jobs, cloud data engineer jobs, data architect jobs, DataOps engineer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem-solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people also for your interviews. You people can download all 6 PDFs in a single zip file from below given links.
Category 5. Validation blind spot incidents.
This category focuses on failures where migration validation appears successful, but hides real inconsistencies. Row counts match, checksums pass, dashboards look stable, yet business truth is already fractured. These incidents show why validation without semantic and performance awareness creates dangerous false safety.
Validation blind spot scenarios.
The following incidents demonstrate how validation can mislead teams during Redshift migration. 1. Row counts match but KPIs differ. 2. Checksums pass but joins fail. 3. Sampling misses edge cases. 4. Deletes not validated. 5. Derived tables not reconciled. 6. BI semantic layer masks inconsistencies. 7. Only recent data validated. 8. Business trusts early dashboards prematurely. 9. Post-migration query plan or performance regressions masked by initial validation. Validation that ignores semantics, joins, and execution behavior creates false confidence.
Real-world incident during source to Redshift migration 32. Row counts match, but KPIs differ after cut.
During an AWS Redshift migration, validation checks showed perfect row count parity between the source system and Redshift. Confident in the results, the team proceeded with cutover. Days later, business KPIs such as revenue, conversion rate, and churn began to diverge from pre-migration benchmarks. The migration was technically complete but analytically incorrect. Failure class, validation blind spot incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system read-only for analytics, historically authoritative for KPI definitions. 2. Redshift cluster fully loaded and declared primary analytical system. 3. CDC pipeline completed and decommissioned after row count validation. 4. BI tools reported to Redshift and publishing dashboards externally. 5. Declared source of truth Redshift for analytics. 6. Authority status, formally transferred based on row count validation alone. Authority was transferred using structural validation instead of semantic validation.
Incident analysis and root cause.
This failure resulted from a flawed validation strategy. 1. Triggering action declaring migration success based solely on row count equality across tables. 2. Why it appeared safe, counts matched exactly and CDC completed without errors. 3. What teams noticed first, business KPIs in Redshift no longer matched historical trends. 4. What teams did not notice, metric definitions depended on joins, filters, and aggregations not validated during migration. 5. How divergence accumulated, KPI logic amplified small semantic differences into large business deltas over time. 6. Missing invariant metric equivalence must be validated, not inferred from row parity.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it creates false confidence at the exact moment authority is transferred. All operational signals appear green, yet business truth is already wrong. Detection latency is often weeks, discovered only when leadership questions unexplained KPI shifts.
What exactly broke? Consistency breakdown.
Semantic and domain-level consistency are broken. Metrics computed in Redshift no longer represent the same business meaning as in the source system. If we roll back only data, this inconsistency remains because the metric interpretation itself has changed, not the raw rows.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Has Redshift accepted analytical authority? Yes, KPIs published. 2. Have dashboards influenced decisions externally? Yes, trust already leaked. 3. Is the original KPI logic versioned and reproducible? Often no. 4. Would snapshot restore change metric behavior? No, logic unchanged. 5. Can authority be cleanly reverted? No, business confidence fractured. Rollback restores rows, not meaning.
Decision point, rollback versus forward fix.
Rollback is technically possible but analytically meaningless. Restoring a snapshot reproduces the same KPI drift because the semantic logic has already changed. Forward fix focused on metric reconciliation and trust rebuilding is the only viable path.
Rollback architecture, why rollback fails here.
Rollback would require restoring a pre-cutover snapshot and repointing BI tools back to the source system. However, because KPIs are defined through aggregations and joins that differ semantically, rollback recreates the same inconsistency. CDC replay cannot fix interpretation drift. BI cache invalidation does not undo business decisions already made. Governance typically blocks rollback because it does not restore analytical truth.
Code illustration and Redshift artifacts.
In this section, we will show 1. How row counts appear correct while KPIs diverge. 2. How aggregate logic produces different business results. 3. Why checksum-style validation misses semantic errors. 4. Why rollback cannot correct KPI interpretation. Validation that ignores metrics validates nothing. Here is Redshift SQL showing how row counts match, while revenue KPIs differ. Disclaimer: always test code in a non-production environment. This snippet proves structural parity. Matching row counts create the illusion that migration succeeded, even though no business meaning has been validated. Here is Redshift SQL showing how KPI aggregation diverges despite matching row counts. Disclaimer: always test code in a non-production environment. This aggregation exposes semantic drift. Small differences in filtering, null handling, or joins produce materially different KPIs even when raw rows match. Here is Redshift SQL showing how join logic alters KPI outcomes. Disclaimer: always test code in a non-production environment. This join changes metric scope. If customer status logic differs from the source, KPIs diverge even though the underlying orders table is identical. Here is Redshift SQL showing why checksum-style validation misses KPI errors. Disclaimer: always test code in a non-production environment. This checksum passes even when KPIs are wrong. It validates row presence, not analytical meaning, proving why checksum-based validation creates false safety.
Containment and forward fix strategy.
Once KPI divergence is confirmed, containment must precede repair. 1. Freeze KPI publication until semantic equivalence is proven. 2. Reconcile KPI logic against the source system definition. 3. Rerun historical metrics side by side for trust rebuilding. 4. Version and lock metric definitions post-migration. 5. Recertify Redshift as authoritative only after metric parity. Business trust is rebuilt through metrics, not counts.
Interview framing, extremely important.
Explain that row counts validate storage, not business truth. Emphasize that KPIs amplify small semantic differences. State clearly why rollback cannot fix meaning drift. Anchor the lesson on metric equivalence as a migration invariant.
Follow-up 1. Why do row counts pass while KPIs fail?
Answer: row counts validate only the presence of records, not how those records participate in business logic. KPIs depend on filters, joins, and aggregation semantics. When any of those differ, metrics drift even though counts remain identical. This makes row count validation dangerously incomplete.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once Redshift KPIs were published and trusted externally. At that point, authority transferred based on incorrect validation. Restoring snapshots would reproduce the same semantic errors without restoring confidence.
Follow-up 3. What single control would have prevented this?
Answer: mandatory KPI-level reconciliation before authority transfer. Migration success should require metric parity over meaningful historical windows, not just row or checksum validation.
Pro insider tip.
If your validation checklist does not include KPI parity, your migration is already unvalidated, even if every row matches.
Real-world incident during source to Redshift migration 33. Checksums pass, but joins fail after cutover.
During an AWS Redshift migration, teams validated data correctness using table-level checksums and hash totals. All checksum comparisons matched between the source system and Redshift, leading to formal cutover approval. After go-live, analysts discovered that key joins produced fewer rows and incorrect KPIs. The data was present, but relational truth was broken. Failure class: validation blind spot incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was: 1. Source system, read-only for analytics and historically authoritative for relational logic. 2. Redshift cluster fully loaded and declared authoritative based on checksum validation. 3. CDC pipeline completed and decommissioned after checksum parity checks. 4. BI tools repointed to Redshift and publishing joined datasets. 5. Declared source of truth, Redshift for analytics. 6. Authority status, transferred based on row and checksum validation only. Relational correctness was inferred from structural equality.
Incident analysis and root cause.
This failure resulted from an incomplete validation invariant. 1. Triggering action approving cutover after checksum and hash totals matched across systems. 2. Why it appeared safe, checksums gave a strong mathematical signal of data equality. 3. What teams noticed first, joined reports showed missing rows and unexpected nulls. 4. What teams did not notice, join keys had subtle differences in null handling, trimming, or casting. 5. How divergence accumulated. Each downstream join amplified small key mismatches into major analytical gaps. 6. Missing invariant, referential equivalence must be validated, not inferred from checksums.
Why this failure is dangerous, hidden risk.
This failure is dangerous because checksums provide a false sense of mathematical certainty. Hashes confirm that rows exist, but say nothing about how those rows relate to each other. Detection latency is often high, surfacing only when cross-table analytics or audits fail.
What exactly broke? Consistency breakdown.
Referential and domain-level consistency are broken. Tables are individually correct, but relationships between them are not. If we roll back only data, this inconsistency remains because the join semantics, not the stored rows, are incorrect.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Has Redshift accepted analytical authority? Yes, joined outputs published. 2. Have downstream systems persisted joined results? Likely derived data exists. 3. Would snapshot restore change join behavior? No, schema and logic unchanged. 4. Are original join semantics fully versioned? Often no. 5. Can authority be reverted without confusion? No, trust already fractured. Rollback restores tables, not relationships.
Decision point, rollback versus forward fix.
Rollback is technically possible but analytically ineffective. Restoring a snapshot reproduces the same join failures because the underlying relational semantics remain unchanged. Forward fix focused on join correction and trust rebuilding is the only viable option.
Rollback architecture. Why rollback fails here.
Rollback would involve restoring a pre-cutover snapshot and repointing BI tools back to the source system. However, because checksum validation already approved structurally identical but relationally incorrect data, rollback reproduces the same failure. CDC replay does not alter join behavior. BI cache invalidation does not undo decisions based on incomplete joins. Governance typically rejects rollback because it does not restore analytical correctness.
Code illustration and Redshift artifacts.
In this section, we will show 1. How checksums validate rows but ignore relationships. 2. How joins silently drop rows despite checksum parity. 3. Why referential drift is invisible to hash-based validation. 4. Why rollback cannot repair join semantics. Checksums validate existence, not truth. Here is Redshift SQL showing checksum parity across tables. Disclaimer: always test code in a non-production environment. This snippet proves checksum parity. It confirms that all order rows exist in Redshift, creating false confidence that migration is correct. Here is Redshift SQL showing how joins silently drop valid rows. Disclaimer: always test code in a non-production environment. This join exposes the failure. Even though both tables pass checksum validation, key mismatches cause valid rows to disappear during joins. Here is Redshift SQL showing null and casting differences, causing join failure. Disclaimer: always test code in a non-production environment. This snippet proves semantic mismatch in join keys. Differences in trimming, null handling, or casting break relationships without affecting checksums. Here is Redshift SQL showing why checksum validation misses join failures. Disclaimer: always test code in a non-production environment. This count remains stable even when joins fail. It demonstrates why structural validation cannot detect relational corruption.
Containment and forward fix strategy.
Once join failure is confirmed, containment must precede repair. 1. Freeze publication of join datasets immediately. 2. Reconcile join keys and null semantics against the source system. 3. Backfill affected joins using corrected logic. 4. Rerun historical analytics side by side for trust rebuilding. 5. Recertify Redshift only after referential parity is proven. Relationships define analytics, not rows.
Interview framing, extremely important.
Explain that checksums validate storage, not relationships. Emphasize that joins are where business truth emerges. State clearly why rollback cannot fix relational semantics. Anchor the lesson on referential equivalence as a migration invariant.
Follow-up 1. Why do checksums pass while joins fail?
Answer: checksums confirm that rows exist, but they ignore how rows relate across tables. Joins depend on key semantics, null handling, and casting. When those differ, relationships break even though the data itself is intact. This makes checksum-only validation dangerously misleading.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once joined analytics were published and trusted. At that point, restoring snapshots would reproduce the same relational errors without restoring confidence or authority.
Follow-up 3. What single control would have prevented this?
Answer: mandatory join-level validation before cutover. Migration success must require referential parity checks across all critical joins, not just row or checksum equality.
Pro insider tip.
If your validation proves tables but not joins, you validated storage, not analytics.
Real-world incident during source to Redshift migration 34. Sampling-based validation missed edge case data corruption.
During an AWS Redshift migration, teams validated data correctness using sampled subsets of large fact tables to accelerate cutover decisions. While sampled rows matched perfectly between source and Redshift, rare but business-critical edge cases were excluded from validation. After cutover, downstream reports exposed inconsistencies tied to outlier records that were never sampled. Failure class: validation blind spot incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system, historically authoritative and fully populated with edge case records. 2. Redshift cluster, fully loaded and declared correct based on sampled validation. 3. CDC pipeline, completed and decommissioned post-validation. 4. Validation approach, random and percentage-based sampling of large tables. 5. BI tools, repointed to Redshift immediately after validation approval. 6. Declared source of truth, Redshift for analytics. 7. Authority status, transferred based on partial visibility of data. Sampling validated what was seen, not what mattered.
Incident analysis and root cause.
This failure resulted from a flawed validation assumption. 1. Triggering action, approving migration correctness based on sampled data comparisons. 2. Why it appeared safe, sampled rows showed perfect parity across all checked attributes. 3. What teams noticed first, discrepancies limited to rare conditions and extreme values. 4. What teams did not notice, that edge cases were systematically excluded from samples. 5. How divergence accumulated. Business logic amplified small edge case gaps into visible KPI errors. 6. Missing invariant. Validation must cover boundary and edge case conditions, not averages.
Why this failure is dangerous, hidden risk.
This failure is dangerous because sampling creates statistical confidence, not correctness guarantees. Most dashboards look correct, delaying detection. Detection latency is often weeks, surfacing only when rare events, audits, or regulatory cases rely on unsampled data.
What exactly broke? Consistency breakdown.
Domain level and analytical consistency are broken. Core datasets are mostly correct, but specific business conditions are wrong. If we roll back only data, this inconsistency remains because the validation logic, not the stored data, was incomplete.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Has Redshift been declared analytically authoritative? Yes, based on samples. 2. Have downstream reports used edge case sensitive data? Yes, errors discovered. 3. Would Snapshot Restore include missing edge cases? Yes, but indistinguishable. 4. Is the validation logic itself corrected? No, sampling flaw persists. 5. Can authority be restored without revalidation? No, trust already weakened. Rollback restores data, not confidence in validation.
Decision point, rollback versus forward fix.
Rollback is technically possible but insufficient on its own. Restoring snapshots without changing validation strategy reproduces the same blind spots. Forward fix focused on targeted boundary validation is required to restore trust.
Rollback architecture. Why rollback alone is insufficient.
Rollback would involve restoring a pre-cut over snapshot and repointing BI tools back to the source system. CDC replay would not alter which records are sampled. Without changing validation methodology, rollback simply resets the system to a state where edge cases remain unverified. Governance often rejects rollback because it does not address the root validation failure.
Code illustration and Redshift artifacts.
In this section, we will show 1. How boundary values expose data mismatches missed by sampling. 2. Why sampled validation falsely indicated migration success. Sampling proves averages, not correctness. Forensic audit, proving sampling blindness via boundary analysis. Disclaimer, always test code in a non-production environment. This audit query identifies sampling blindness. It exposes extreme outliers that random sampling typically misses. If these min or max values do not match the source system exactly, it proves that correctness was only an illusion based on a biased subset of data. Here is Redshift SQL showing mismatches isolated to rare conditions. Disclaimer, always test code in a non-production environment. This snippet isolates rare, high-impact records. Discrepancies here confirm that sampling-based validation missed critical edge cases.
Containment and forward fix strategy.
Once sampling blindness is confirmed, containment must precede repair. 1. Suspend trust in analytics relying on sampled validation. 2. Identify and enumerate all business-critical edge conditions. 3. Revalidate full datasets for boundary and rare value cases. 4. Backfill or correct affected aggregates and reports. 5. Redefine validation criteria before any future cutover. Correctness lies at the edges, not the mean.
Interview framing, extremely important.
Explain why sampling validates probability, not correctness. Highlight how edge cases carry disproportionate business impact. State why rollback without better validation is ineffective. Anchor the lesson on boundary-driven validation invariance.
Follow-up 1. Why did sampling miss this issue?
Answer: sampling optimizes for speed, not coverage. Rare or extreme values have a low probability of appearing in samples, yet they often drive the most critical business outcomes. This makes sampling insufficient for migration validation.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once analytics were trusted based on sampled validation. At that point, restoring snapshots without redefining validation would reproduce the same blind spots.
Follow-up 3. What single control would have prevented this?
Answer: mandatory boundary and edge case validation. Migration sign-off must require explicit checks on rare, extreme, and business-critical conditions, not just representative samples.
Pro insider tip.
If your validation strategy ignores edge cases, your migration will fail exactly where the business cares most.
Real-world incident. During source to Redshift migration 35, deletes were not validated during migration.
During an AWS Redshift migration, validation focused on row counts, aggregates, and recent inserts, but delete operations were never explicitly validated. As a result, rows that had been deleted in the source system continued to exist in Redshift as ghost records, silently corrupting analytics after cutover. Failure class: validation blind spot incident.
System state before failure. Very important.
At the moment the failure was introduced, the system state was: 1. Source system fully authoritative with active delete operations. 2. Redshift cluster loaded via snapshot and CDC assumed delete complete. 3. CDC pipeline running but delete validation not explicitly checked. 4. Validation scope focused on inserts and aggregates only. 5. BI tools repointed to Redshift after validation sign-off. 6. Declared source of truth, Redshift for analytics. 7. Authority status transferred without delete completeness proof. Deletes are invisible unless you explicitly look for absence.
Incident analysis and root cause.
This failure resulted from a critical validation omission. 1. Triggering action approving migration without validating delete propagation. 2. Why it appeared safe, row counts and KPIs matched expected values. 3. What teams noticed first, overcounted entities and resurrected historical records. 4. What teams did not notice that deleted source rows still existed in Redshift. 5. How divergence accumulated. Ghost rows persisted and polluted downstream aggregates. 6. Missing invariant. Validation must prove both presence and absence of records.
Why this failure is dangerous. Hidden risk.
This failure is dangerous because deletes reduce data, not add it. Most validations look for missing data, not extra data. Dashboards look healthy, counts appear stable, and detection latency is often weeks until reconciliation or audits surface inflated results.
What exactly broke? Consistency breakdown.
Domain level and analytical consistency are broken. Redshift contains records that no longer exist in the source system. If we roll back only data, this inconsistency remains because rollback restores data snapshots without guaranteeing delete correctness.
Rollback viability checklist. Go or no go.
Before rollback is considered, the architect must evaluate: 1. Have deletes already been missed in Redshift? Yes, ghost rows exist. 2. Can deleted records be deterministically identified, sometimes business key dependent? 3. Would snapshot restore guarantee delete correctness? No, validation gap persists. 4. Have downstream systems consumed inflated data? Likely. 5. Can authority be restored without delete reconciliation? No, trust impacted. Rollback restores state, not absence guarantees.
Decision point. Rollback versus forward fix.
Rollback is technically possible but insufficient. Restoring a snapshot without explicit delete reconciliation reproduces the same risk. Forward fix focused on identifying and removing ghost rows is required to restore analytical trust.
Rollback architecture. Why rollback does not solve this?
Rollback would involve restoring a pre-cut over snapshot and repointing BI tools. However, unless delete propagation is explicitly revalidated or reconciled against the source, ghost rows will persist or reappear. Governance teams often reject rollback because it resets time without fixing delete blind spots.
Code illustration and Redshift artifacts.
In this section, we will show: 1. How ghost rows are detected using existence checks. 2. Why row counts and aggregates failed to expose delete loss. Deletes fail silently unless absence is validated. Here is Redshift SQL exposing ghost rows that were deleted in the source. Disclaimer: always test code in a non-production environment. This snippet detects rows that exist in Redshift, but no longer exist in the source system. These ghost rows prove that deletes were not correctly propagated or validated.
Containment and forward fix strategy.
Once ghost rows are confirmed, containment must precede repair. 1. Suspend trust in analytics dependent on affected tables. 2. Identify ghost rows using authoritative source comparisons. 3. Purge invalid records with full audit logging. 4. Rebuild aggregates and derive tables. 5. Add delete validation as a mandatory migration gate. Absence must be validated as rigorously as presence.
Interview framing, extremely important.
Explain why deletes are harder to validate than inserts. Highlight how row counts can increase correctness illusion. State why rollback alone cannot fix delete blind spots. Anchor the lesson on validating absence explicitly.
Follow-up 1. Why didn't row counts catch this?
Answer: row counts validate volume, not correctness. If deletes are missed, row counts may still look reasonable or even correct relative to expectations. The error lies in excess data, not missing data.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once analytics and reports consumed ghost rows. At that point, restoring snapshots without delete reconciliation perpetuates inflated results and erodes trust.
Follow-up 3. What single control would have prevented this?
Answer: mandatory delete validation using existence checks. Migration sign-off must prove that records removed from the source are also absent from the target.
Pro insider tip.
If you never validate deletes, assume your warehouse contains data that should not exist.
Real-world incident during source to Redshift migration 36. Derived tables were not reconciled after migration.
During an AWS Redshift migration, base tables were validated and signed off, but derived tables such as aggregates, summary tables, and materialized views were not reconciled against the source system. As a result, downstream analytics consumed derived data that no longer matched the underlying business reality. Failure class: validation blind spot incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was: 1. Source system authoritative for both base and derived reporting tables. 2. Redshift cluster loaded with base tables validated successfully. 3. Derived tables rebuilt or refreshed only on Redshift. 4. CDC pipeline applied changes only to base tables. 5. BI tools querying derived tables for performance. 6. Declared source of truth Redshift for analytics. 7. Authority status assumed inherited from base table validation. Derived correctness cannot be inferred from base correctness.
Incident analysis and root cause.
This failure occurred due to incomplete validation scope. 1. Triggering action, signing off migration after validating only base tables. 2. Why it appeared safe, base tables matched row counts and checksums. 3. What teams noticed first, KPI discrepancies across dashboards using derived tables. 4. What teams did not notice that derived tables were built using different logic or timing. 5. How divergence accumulated. Derived tables drifted as CDC updates arrived without full recomputation. 6. Missing invariant derived data must be validated independently, not inferred.
Why this failure is dangerous, hidden risk.
This failure is dangerous because derived tables often power executive dashboards and downstream systems. Validation appears complete, performance improves, and no alarms fire. Detection latency is typically weeks, surfacing only when independent reports disagree.
What exactly broke? Consistency breakdown.
Analytical and domain-level consistency are broken. Base data may be correct, but derived interpretations are not. If we roll back only data, this inconsistency remains because derived logic and refresh boundaries are still misaligned.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate: 1. Are base tables correct in Redshift? Yes, validated. 2. Are derived tables provably equivalent to source? No, not reconciled. 3. Would snapshot restore fixed derived logic? No, logic mismatch persists. 4. Have downstream systems consumed derived outputs? Likely. 5. Can authority be restored without rebuilding derived data? No. Rollback restores raw data, not derived meaning.
Decision point, rollback versus forward fix.
Rollback is rarely effective because it does not address derived table logic or refresh timing. Forward fix focused on reconciling and rebuilding derived tables from validated base data is the only practical path to restoring trust.
Rollback architecture, why rollback does not solve this.
Rollback would involve restoring a snapshot and repointing BI tools. However, unless derived tables are rebuilt using validated logic and synchronized timing, the same inconsistencies reappear. Governance teams often reject rollback because it delays insight without fixing derived correctness.
Code illustration and Redshift artifacts.
In this section, we will show 1. How derived tables diverge from their base tables. 2. Why base table validation alone was insufficient. Dependencies must be validated, not assumed. Here is Redshift SQL proving derived table mismatch against base data. Disclaimer: always test code in a non-production environment. Comparing aggregates from base tables to derived summaries exposes divergence. Even when base data is correct, derived tables can drift due to refresh timing or logic differences.
Containment and forward fix strategy.
Once derived inconsistency is confirmed, containment must precede repair. 1. Suspend trust in dashboards powered by derived tables. 2. Rebuild derived tables from validated base data. 3. Align refresh timing with CDC application boundaries. 4. Reconcile results against source-derived equivalents. 5. Add derived table validation to migration sign-off criteria. Derived data is logic, not just storage.
Interview framing, extremely important.
Explain why base table correctness does not guarantee analytical correctness. Highlight derived tables as independent validation units. State why rollback cannot fix logic-level divergence. Anchor the lesson on dependency-aware validation.
Follow-up 1. Why didn't base table validation catch this?
Answer: base table validation proves raw data correctness only. Derived tables apply additional logic and timing assumptions that can drift independently, making base validation insufficient.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once downstream systems consumed incorrect derived outputs. Restoring snapshots without rebuilding derived tables perpetuates analytical errors.
Follow-up 3. What single control would have prevented this?
Answer: mandatory reconciliation of all derived tables against source equivalents before declaring analytical authority. Dependencies must be validated explicitly.
Pro insider tip.
If you don't reconcile derived tables, you are validating storage, not meaning.
Real-world incident during source to Redshift migration 37. BI semantic layer masked underlying data inconsistencies.
During an AWS Redshift migration, BI tools were repointed to Redshift using an existing semantic layer that applied metric definitions, joins, and filters abstracted from the physical tables. While underlying data inconsistencies existed, the semantic layer continued to return stable-looking KPIs, masking corruption and creating false confidence. Failure class: validation blind spot incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system authoritative with validated business metrics. 2. Redshift cluster receiving migrated data with unresolved inconsistencies. 3. CDC pipeline running with acceptable lag. 4. BI semantic layer reused without revalidation. 5. BI dashboards showing stable KPIs derived from semantic logic. 6. Declared source of truth, implicitly Redshift for analytics. 7. Authority status assumed via BI outputs, not data validation. Abstraction can hide corruption better than dashboards reveal it.
Incident analysis and root cause.
This failure resulted from misplaced trust in abstraction. 1. Triggering action, reusing the BI semantic layer without validating its assumptions against Redshift data. 2. Why it appeared safe, dashboards continued to show stable KPIs with no obvious anomalies. 3. What teams noticed first, discrepancies surfaced only when raw exports were compared manually. 4. What teams did not notice that joins, filters, and metric definitions were compensating for missing or duplicated data? 5. How divergence accumulated. The semantic layer normalized inconsistencies into believable results. 6. Missing invariant. Analytical truth must be validated below the semantic layer.
Why this failure is dangerous, hidden risk.
This failure is dangerous because semantic layers are designed to stabilize outputs. They smooth over data defects, hide missing joins, and apply business rules that conceal inconsistencies. Detection latency is often measured in months, discovered only during audits or reconciliation outside BI.
What exactly broke? Consistency breakdown.
Analytical and semantic consistency are broken. The BI layer presents a coherent narrative that does not reflect the underlying data state. If we roll back only data, this inconsistency remains because the semantic layer continues to reinterpret corrupted inputs into stable-looking outputs.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Has Redshift accepted analytical rights? No read-only analytics. 2. Are BI semantic definitions validated against Redshift data? No. 3. Have business decisions relied on semantic KPIs? Yes, trust already formed. 4. Can rollback expose hidden inconsistencies? No, semantic layer persists. 5. Can authority be restored without semantic revalidation? No. Rollback restores data state, not analytical meaning.
Decision point, rollback versus forward fix.
Rollback is rarely effective because it does not invalidate or correct semantic interpretations already trusted by the business. Forward fix must focus on semantic layer revalidation and controlled re-exposure of analytics after raw data correctness is proven.
Rollback architecture, why rollback does not solve this.
Rollback would involve restoring a prior snapshot and repointing BI tools. However, unless the semantic layer is revalidated and possibly rebuilt, dashboards will continue to present misleading stability. Governance teams often reject rollback because it disrupts reporting without addressing semantic distortion.
Containment and forward fix strategy.
Once semantic masking is identified, containment must precede repair. 1. Freeze semantic layer changes in dashboards. 2. Validate raw Redshift tables independently of BI abstractions. 3. Audit semantic joins, filters, and metric logic against data reality. 4. Rebuild or adjust semantic models where assumptions no longer hold. 5. Reintroduce dashboards gradually with explicit trust disclaimers. Semantic correctness must be earned, not assumed.
Interview framing, extremely important.
Explain how BI abstraction can hide data corruption. State why validation must occur below the semantic layer. Highlight that stable dashboards do not imply correct data. Anchor the lesson on authority over interpretation.
Follow-up 1. Why didn't dashboards show obvious errors?
Answer: semantic layers are built to normalize and stabilize outputs. They apply joins, filters, and defaults that can compensate for missing or duplicated data, masking underlying corruption.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once business users trusted semantic KPIs. Even after data restoration, the same semantic logic would continue producing misleading confidence.
Follow-up 3. What single rule would have prevented this?
Answer: never validate analytics through the semantic layer alone. Raw data must be validated independently before semantic abstraction is trusted.
Pro insider tip.
If your first validation query runs in a BI tool, you already validated too late.
Real-world incident during source to Redshift migration 38. Only recent data was validated during migration.
During an AWS Redshift migration, validation efforts focused exclusively on recent data ranges to accelerate business sign-off. Historical data was assumed correct because snapshots completed successfully and CDC showed low lag. As a result, long-tail historical inconsistencies were never detected and silently propagated into production analytics. Failure class: validation blind spot incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was: 1. Source system authoritative with long historical data range. 2. Redshift cluster loaded with full snapshot and ongoing CDC. 3. CDC pipeline running with low lag focused on recent changes. 4. Validation scope limited to recent days or weeks only. 5. BI tools enabled for recent period reporting. 6. Declared source of truth. Redshift for validated ranges only. 7. Authority status implicitly assumed for all time ranges. Validating recency does not validate history.
Incident analysis and root cause.
This failure emerged from a scoped validation assumption. 1. Triggering action restricting validation queries to recent time windows to meet cutover timelines. 2. Why it appeared safe recent metrics match closely between source and Redshift. 3. What teams noticed first historical reports showed unexplained discrepancies when accessed later. 4. What teams did not notice that older partitions were never reconciled at all. 5. How divergence accumulated, snapshot and early CDC errors in historical ranges remained permanently undetected. 6. Missing invariant, validation must cover the full historical domain, not just recent activity.
Why this failure is dangerous, hidden risk.
This failure is dangerous because recent data correctness creates false confidence about the entire dataset. Monitoring remains green, KPIs appear correct, and business confidence grows. Detection latency is often months, surfacing only when long-term trends, audits, or backdated analyses are required.
What exactly broke? Consistency breakdown.
Temporal and analytical consistency are broken across historical ranges. Recent data is trustworthy, while older data is not. If we roll back only data, this inconsistency remains because the validation blind spot allowed historical corruption to persist unchallenged.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Has Redshift accepted writes? No, analytics only. 2. Were historical ranges ever validated? No, blind spot confirmed. 3. Can a rollback selectively target historical corruption? No, mixed trust state. 4. Have downstream systems consumed historical analytics? Likely. 5. Can authority be restored without full revalidation? No. Rollback reset state, not forgotten validation.
Decision point, rollback versus forward fix.
Rollback rarely restores trust because it does not retroactively validate historical data. Forward fix is required, focused on full-range reconciliation and explicit disclosure of historical uncertainty until verification is complete.
Rollback architecture, why rollback does not solve this.
Rollback would involve restoring a prior snapshot and repointing BI tools. However, because historical ranges were never validated, rollback merely reintroduces an equally unverified state. Governance teams often reject rollback in favor of controlled historical reconciliation.
Code illustration and Redshift artifacts.
In this section, we will show 1. How historical time ranges are compared to detect unvalidated gaps. History ignored is corruption delayed. Here is Redshift SQL showing historical ranges that were never validated during migration. Disclaimer: always test code in a non-production environment. This snippet exposes the full temporal range of data in Redshift. Comparing this to the validation window proves that large historical segments were never reconciled, creating a permanent blind spot.
Containment and forward fix strategy.
Once historical blind spots are confirmed, containment must precede repair. 1. Suspend trust in historical analytics explicitly. 2. Revalidate data across full historical ranges in controlled phases. 3. Reconcile discrepancies with source system records. 4. Annotate reports to distinguish validated versus unvalidated periods. 5. Only restore full trust after historical parity is proven. Unvalidated history is technical debt with interest.
Interview framing, extremely important.
Explain why validating only recent data creates false confidence. Describe how historical blind spots evade detection for months. Emphasize that snapshots do not validate correctness by themselves. Anchor the lesson on full domain validation.
Follow-up 1. Why did recent validations pass while history was wrong?
Answer: recent data was replicated and validated under active monitoring, while historical data relied entirely on snapshot assumptions. Without explicit checks, historical corruption remained invisible.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe once business users trusted analytics without knowing that large historical ranges were never validated. At that point, authority was assumed without evidence.
Follow-up 3. What single control would have prevented this?
Answer: mandating validation coverage across the full historical range before cutover. Any unvalidated period should block authority declaration.
Pro insider tip.
If your validation window is shorter than your business memory, your migration is already lying.
Real-world incident during source to Redshift migration 39. Business trusted early dashboards prematurely.
During an AWS Redshift migration, early BI dashboards built on Redshift were shared with business stakeholders to demonstrate progress. Although validation was incomplete and authority had not been formally declared, business users began using these dashboards for decisions. This prematurely established Redshift as the perceived source of truth, irreversibly damaging rollback viability. Failure class: validation blind spot incident.
System state before failure, very important.
At the moment authority was unintentionally transferred, the system state was: 1. Source system fully authoritative and rights enabled. 2. Redshift cluster partially validated analytics only. 3. CDC pipeline running with acceptable lag. 4. BI tools enabled on Redshift for demonstration purposes. 5. Validation status incomplete and ongoing. 6. Declared source of truth not formally declared. 7. Authority status implicitly shifted through business usage. Authority moved socially before it moved technically.
Incident analysis and root cause.
This failure resulted from a governance breakdown, not a system failure. 1. Triggering action sharing early Redshift dashboards with business stakeholders. 2. Why it appeared safe metrics appeared reasonable and closely matched expectations. 3. What teams noticed first business discussions and decisions referencing Redshift numbers. 4. What teams did not notice that validation gates had not been completed. 5. How divergence accumulated. Business narratives formed around unvalidated data. 6. Missing invariant: authority must never transfer before validation completion.
Why this failure is dangerous, hidden risk.
This failure is dangerous because trust becomes irreversible. Once dashboards influence decisions, budgets, or forecasts, rollback is perceived as denial rather than correction. Detection latency is immediate in hindsight but invisible at the moment of transfer.
What exactly broke? Consistency breakdown.
Authoritative consistency is broken. The business treats Redshift as truth while engineers still treat it as provisional. If we roll back only data, this inconsistency remains because trust and authority have already migrated socially.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate: 1. Has Redshift accepted rights? No, analytics only. 2. Have dashboards influenced decisions? Yes, authority shifted. 3. Can business decisions be invalidated? No, narrative locked. 4. Is Redshift perceived as the source of truth? Yes. 5. Can authority be reclaimed cleanly? No, trust already transferred. Rollback fails when trust has already moved.
Decision point, rollback versus forward fix.
Rollback is technically possible but organizationally ineffective. Forward fix becomes mandatory, focused on reconciling data discrepancies while preserving business confidence.
Rollback architecture, why rollback does not work here.
A rollback would require retracting dashboards, invalidating decisions, and reasserting the source system as authoritative. In practice, this is rarely accepted. Governance teams typically block rollback once executive trust has formed.
Containment and forward fix strategy.
Once premature trust is established, containment must focus on authority stabilization. 1. Formally declare Redshift as provisional or authoritative immediately. 2. Freeze further metric interpretation until reconciliation completes. 3. Reconcile discrepancies quietly without undermining business confidence. 4. Introduce explicit validation sign-off gates for future phases. 5. Rebuild governance controls around dashboard access. You cannot unshow a dashboard.
Interview framing, extremely important.
Explain that authority can transfer socially before it transfers technically. Describe how dashboards create irreversible trust. Emphasize that rollback is a governance problem, not a database problem. Anchor the lesson on controlled exposure, not faster demos.
Follow-up 1. Why is this not a technical failure?
Answer: because all systems were behaving as designed. The failure occurred when unvalidated outputs were treated as authoritative, bypassing governance controls.
Follow-up 2. When did rollback stop being safe?
Answer: rollback stopped being safe the moment business decisions referenced Redshift dashboards. At that point, authority had already shifted regardless of data correctness.
Follow-up 3. What single rule would have prevented this?
Answer: never expose dashboards without explicit validation and authority disclaimers. Access control is an architectural boundary, not a communication detail.
Pro insider tip.
The first executive screenshot is often the real cutover, not the one in the runbook.
Real-world incident during source to Redshift migration 40. Post-migration query plan and performance regression masked by initial validation.
During an AWS Redshift migration, initial validation focused on row counts and query correctness. Early test queries ran successfully and returned expected results. However, once production workloads ramped up, critical analytical queries degraded severely due to missing distribution keys, sort keys, and outdated statistics. The regression was invisible during validation but catastrophic under real load. Failure class. Validation blind spot incident.
System state before failure, very important.
At the moment the failure was introduced, the system state was 1. Source system optimized with mature indexes and stable query plans. 2. Redshift cluster newly loaded with migrated data but default physical design. 3. Distribution and sort keys not yet tuned for production workloads. 4. Statistics state incomplete or stale after bulk load. 5. CDC pipeline running normally. 6. BI and downstream systems gradually ramping up traffic. 7. Declared source of truth, Redshift for analytics. 8. Authority status, technically transferred without performance validation. Correct results under light load do not imply correct execution under real load.
Incident analysis and root cause.
This failure emerged from a validation scope gap. 1. Triggering action declaring migration success based on functional query correctness. 2. Why it appeared safe validation queries returned correct results with acceptable latency. 3. What teams noticed first, severe slowdowns and timeouts once concurrency increased. 4. What teams did not notice that execution plans had fundamentally changed from the source system. 5. How divergence accumulated, production traffic amplified inefficient joins, scans, and data shuffles. 6. Missing invariant, query performance characteristics must be validated under representative load.
Why this failure is dangerous, hidden risk.
This failure is dangerous because it passes every correctness check. Queries return the right answers, dashboards load during testing, and no data errors are visible. The problem surfaces only under concurrency and scale, often after the business has already committed to the new platform. Detection latency is usually days to weeks.
What exactly broke? Consistency breakdown.
Execution and performance consistency are broken. The analytical system can no longer answer business questions within required time bounds. If we roll back only data, this inconsistency remains because physical execution characteristics, not data values, are the source of failure.
Rollback viability checklist, go or no go.
Before rollback is considered, the architect must evaluate. 1. Has Redshift accepted analytical traffic? Yes, workloads active. 2. Are query plans fundamentally different from source? Yes. 3. Can performance issues be fixed without restore? Often yes. 4. Would rollback restore source performance immediately? Yes. 5. Is rollback acceptable to the business? Often no. Performance regressions weaken rollback but do not always block it.
Decision point, rollback versus forward fix.
Rollback remains technically possible because data correctness is intact. However, businesses often prefer forward fix because restoring physical design is less disruptive than reverting analytics back to the source system.
Rollback architecture, if executed.
Rollback would require restoring the Redshift cluster from a pre-cutover snapshot or fully repointing analytics back to the source system. BI caches must be invalidated, downstream extracts discarded, and governance approval obtained due to reporting disruption. Partial rollbacks are avoided because performance issues are systemic, not table-specific.
Code illustration and Redshift artifacts.
In this section, we will show 1. How execution plans changed post-migration. 2. How table distribution and sort keys differ from expectations. 3. How runtime metrics expose hidden performance regressions. 4. How forward fix restores performance without data rollback. Performance failures must be proven at the execution layer. Forensic audit. Detecting cross-node shuffle via execution plans. Disclaimer: always test code in a non-production environment. This ds_dist_both marker is the smoking gun. It proves that Redshift is forced to move both tables across the network to perform the join. This physical shuffle kills performance and indicates a failure in the distribution strategy that row counts could never detect. Here is Redshift system table, SQL showing distribution, and sort key misalignment. Disclaimer: always test code in a non-production environment. High skew confirms uneven data distribution. This amplifies query latency under load and explains why validation queries appeared fast but production queries degraded. Here is Redshift runtime metrics, SQL showing production time query degradation. Disclaimer: always test code in a non-production environment. This metric proves that execution time exploded under concurrency. The data itself is correct, but the execution path is no longer viable for business SLAs. Here is forward fix SQL showing how correcting physical design restores performance. Disclaimer: always test code in a non-production environment. Aligning distribution and sort keys with join patterns eliminates unnecessary redistribution. This forward fix restores performance without changing data values.
Containment and forward fix strategy.
Once performance regression is confirmed, containment must focus on execution safety. 1. Throttle or queue heavy workloads temporarily. 2. Identify top offending queries via system tables. 3. Correct distribution and sort keys on critical tables. 4. Refresh statistics after physical changes. 5. Revalidate performance under production-like concurrency. Performance trust must be earned under real load.
Interview framing, extremely important.
Explain why correctness validation is insufficient without performance validation. Describe how execution plans change across systems. Highlight that physical design is part of data correctness. Anchor the lesson on validating under representative load.
Follow-up 1. Why didn't validation catch this?
Answer: validation ran under light load and focused on correctness, not execution behavior. Query plans only become pathological when data volume and concurrency increase.
Follow-up 2. When did rollback stop being attractive?
Answer: rollback became unattractive once data correctness was confirmed and the business depended on Redshift. At that point, fixing physical design was less disruptive than reverting platforms.
Follow-up 3. What single rule would have prevented this?
Answer: never declare migration success until critical queries are validated under production-like load, with execution plans reviewed.
Pro insider tip.
If you never ran explain during migration, you validated results, not the system.
Part 1 wrap-up, where rollback quietly breaks.
Every incident in Part 1 shares a dangerous illusion. On the surface, nothing looks broken. 1. Systems respond and dashboards load normally. 2. Technical validation passes character for character. 3. Unchecked assumptions erode rollback viability silently. 4. Rollback is treated as a safety net instead of a technical contract. Migrations quietly cross the line without alarms, errors, or consensus.
Part 2 introduction, the point of no return.
Part 2 begins after that line has been crossed. Rollback is no longer theoretical, it is provably impossible because 1. Data has been consumed by external partners. 2. Regulatory reports have been formally submitted. 3. ML models have been trained on inconsistent data. 4. Downstream systems have persisted a corrupted state. Part 2 focuses on containment and forward fix, the only options left once rollback is dead.
Next step, master the point of no return in Part 2.
Part 1 explored how the illusion of safety erodes. Part 2 enters the high-stakes reality of irreversible failure. To continue your journey, 1. Find the direct link to Part 2 in the video description or the pinned comment below. 2. We will dissect 90+ advanced scenarios covering regulatory submission errors and ML model corruption. 3. Learn the forward fix strategies that only principal architects use when snapshots are no longer an option. Do not miss the conclusion of this series. Subscribe now and proceed to Part 2.
For more exciting tips, tricks, and more importantly, for valuable insights of interviews, please share, like, and subscribe to my channel. It has a lot of valuable information about various insights of interviews. It has a wide range of real-world portfolio projects of various technologies for interviews, and it has wide range of most asked interview questions and answers of various technologies like data science, SAP, AWS, DevOps, and full-stack web development, and more. That will be useful during interviews. It has a wide range of most asked interview questions and answers and real-world portfolio projects of various technologies for freshers, for 2 to 3 years, experienced candidates, and for 5 or above years, experienced candidates to test their skills by knowing most asked interview questions and make themselves ready for interviews.